may contain as many as 26 satellite galaxies orbiting its periphery, offering insights into the hierarchical formation of galactic structures. One of Andromeda's most remarkable features is its double nucleus, a peculiarity that hints at a complex history of galactic mergers and interactions. The central region of M31 houses a dense collection of stars surrounding a supermassive black hole, estimated to be 140 million times the mass of our Sun. The presence of this black hole fuels fascinating phenomena, including intense radiation bursts and the accretion of stellar material, shedding light on the dynamics of galactic cores. Unlike the Milky Way, Andromeda's spiral arms are relatively well-defined, giving it a classic pinwheel appearance. These arms are teeming with regions of active star formation, where immense clouds of hydrogen gas collapse under their own gravity to form new stars. The galaxy's bright blue clusters, seen in ultraviolet light, are a testament to the ongoing birth of massive, short-lived stars that will eventually explode as supernovae. The older, reddish stars in Andromeda's halo and central bulge tell a different story, one of ancient star systems that have weathered billions of years. These populations provide a glimpse into the early epochs of galactic evolution, helping scientists piece together the history of star formation in our local universe. Perhaps the most tantalizing aspect of the Andromeda galaxy is its impending collision with the Milky Way. Observations reveal that Andromeda is hurtling toward us at a speed of about 110 kilometers per second. In approximately 4.5 billion years, the two galaxies are expected to merge in a spectacular cosmic dance, forming a new elliptical galaxy sometimes referred to as Milkomeda. This collision will be a transformative event, reshaping the structure of both galaxies and igniting a burst of star formation as gas and dust clouds collide. Although such a cataclysm might sound destructive, the vast distances between stars mean that direct stellar collisions are unlikely. Instead, the merger will create tidal tails, intricate streams of stars, and a dramatic reshuffling of galactic components. Andromeda has been studied extensively using both ground-based and space-based telescopes. The Hubble Space Telescope has provided breathtaking images of the galaxy, revealing its intricate spiral structure, star-forming regions, and even individual stars. Future observatories, such as the James Webb Space Telescope and the Extremely Large Telescope, promise to deepen our understanding of Andromeda by studying its stars, planets, and black hole in unprecedented detail. One of the most exciting areas of research involves the search for exoplanets in Andromeda. While detecting planets in another galaxy is extraordinarily challenging, advancements in microlensing techniques and spectroscopy may one day allow us to identify worlds orbiting stars in this neighboring galaxy. Such discoveries could revolutionize our understanding of planetary systems and the potential for life beyond the Milky Way. Andromeda's proximity makes it a valuable reference point for studying galaxies throughout the universe. By examining its structure, composition, and dynamics, astronomers can develop models that apply to galaxies billions of light-years away. The study of Andromeda's dark matter halo, for instance, has implications for understanding the mysterious substance that makes up 85% of the universe's mass. The galaxy also serves as a time capsule, preserving evidence of past interactions with other galaxies. Stellar streams, faint trails of stars torn from satellite galaxies, crisscross Andromeda's halo, offering clues about its history of galactic cannibalism. These remnants of past mergers help astronomers reconstruct the timeline of Andromeda's growth, providing a glimpse into the life cycle of galaxies. Beyond its scientific value, the Andromeda Galaxy has captured the human imagination for centuries. Visible to the naked eye as a faint smudge in the night sky, it has inspired countless myths, artworks, and dreams of intergalactic travel. As our technology advances and our understanding of the cosmos deepens, Andromeda remains a symbol of humanity's insatiable curiosity and our quest to comprehend the universe. Whether through the lens of a telescope or the imagination of a dreamer, the Andromeda Galaxy invites us to ponder profound questions about our place in the cosmos. What stories do its stars tell? What secrets lie hidden within its vast expanse? And what future awaits as our two galaxies converge in a cosmic embrace? The Andromeda Galaxy, or Messier 31, stands as one of the most intriguing and vital cosmic neighbors of the Milky Way. Its staggering proximity of 2.5 million light-years allows astronomers to explore its intricate structure with unprecedented clarity, a window into the processes that govern galaxies across the universe. This massive spiral galaxy, over 220,000 light-years in diameter, surpasses our own Milky Way in size and contains an estimated 1 trillion stars. Its colossal mass and dynamic nature make it a perfect laboratory for studying galaxy formation, star evolution, and the mysterious force of dark matter. Andromeda's double nucleus, a feature visible in its central bulge, has perplexed scientists for decades. This peculiar structure hints at a complex history of mergers and interactions with smaller galaxies. At its core lies a supermassive black hole, approximately 140 million times the mass of the Sun. This black hole exerts a gravitational pull that influences the orbits of nearby stars and triggers high-energy phenomena such as X-ray flares. These intense bursts of radiation illuminate the dynamic and sometimes violent processes that occur in galactic cores. Clouds collapse under gravity to form new stars. Bright blue clusters dot these arms, signifying the presence of massive, young stars that shine intensely before exhausting their fuel and ending their lives in spectacular supernovae. These explosions enrich the galaxy with heavy. The spiral arms of this galactic giant are regions of immense activity, where dense molecular elements, driving the chemical evolution necessary for the formation of planets and, potentially, life. The interstellar medium of Andromeda is also rich with hydrogen gas and cosmic dust, creating vibrant nebulae that serve as the birthplaces of new stars. Unlike our Milky Way, which exhibits a more subtle spiral pattern, Andromeda's arms are well-defined, giving it the iconic shape often associated with galaxies. These arms are not static, they are shaped and reshaped by the gravitational interactions with Andromeda's satellite galaxies. Observations reveal that Andromeda is surrounded by a swarm of smaller galaxies, some of which are being torn apart by its gravitational pull. These interactions create streams of stars, known as tidal tails, that arc through Andromeda's halo, providing clues about its history of mergers and acquisitions. Andromeda is not only a showcase of stellar life and death, but also a treasure trove of ancient stars. Its halo contains some of the oldest stars known, remnants from the earliest epochs of galactic formation. By studying these ancient stellar populations, scientists can trace the history of Andromeda back billions of years, uncovering the conditions that prevailed when the universe was young. These studies also shed light on the processes that shaped our own galaxy, offering a broader context for the evolution of the cosmos. One of the most captivating aspects of Andromeda is its future collision with the Milky Way. Observations of its motion indicate that it is hurtling toward us at a speed of approximately 110 km per second. In about 4.5 billion years, the two galaxies will collide and merge to form a new, larger galaxy. This event, often described as a galactic dance, will dramatically reshape the structure of both galaxies. Stars, gas, and dark matter will be redistributed in a complex interplay of gravitational forces, creating tidal streams and igniting bursts of star formation. Despite the seeming violence of such a merger, the vast distances between individual stars mean that direct collisions between them are unlikely. Instead, the merger will create a new cosmic entity, sometimes referred to as Andromeda, with an elliptical structure and a new center of mass. The Andromeda galaxy has been the focus of numerous scientific missions and observations. The Hubble Space Telescope has provided some of the most detailed images of its structure, capturing its spiral arms, central bulge, and outer halo with stunning clarity. These observations have not only deepened our understanding of Andromeda but also served as a benchmark for studying other spiral galaxies in the universe. Advanced instruments, such as the James Webb Space Telescope, promise to unveil even more secrets, allowing astronomers to study the galaxy's individual stars, planetary systems, and even its dark matter halo with unprecedented precision. The search for exoplanets within Andromeda is a burgeoning field of study. While detecting planets in another galaxy is extraordinarily challenging, techniques such as gravitational microlensing offer a glimpse into this possibility. These methods rely on the bending of light caused by the gravitational field of a planet or star, revealing the presence of celestial objects that would otherwise remain hidden. Discovering exoplanets in Andromeda could revolutionize our understanding of planetary formation, potentially revealing worlds vastly different from those in the Milky Way. Andromeda's immense halo of dark matter extends far beyond its visible disk, influencing the motion of its stars and satellite galaxies. This unseen component constitutes the majority of the galaxy's mass, yet its nature remains one of the greatest mysteries in astrophysics. By studying the distribution and behavior of dark matter in Andromeda, scientists hope to unlock the secrets of this enigmatic substance, which plays a crucial role in the formation and evolution of galaxies throughout the universe. As the largest galaxy in our local group, Andromeda serves as a cosmic mirror, reflecting the processes that govern galaxies on larger scales. Its intricate structure, active star-forming regions, and dynamic interactions with other galaxies provide a microcosm of the universe's complexity. By studying Andromeda, astronomers gain insights into phenomena that apply to galaxies billions of light-years away, bridging the gap between our local universe and the distant cosmos. The Andromeda Galaxy is not just an object of scientific inquiry, it is a source of inspiration and wonder. Its visibility to the naked eye as a faint smudge in the night sky has captivated observers for centuries, from ancient astronomers who catalogued it as a nebula to modern scientists who unravel its mysteries with cutting-edge technology. Andromeda represents humanity's enduring quest to understand the cosmos, a testament to our curiosity and imagination. The Andromeda Galaxy is a beacon of cosmic curiosity, continuously drawing the gaze of astronomers and dreamers alike. Its vastness and complexity defy easy understanding, inviting deeper exploration with every new discovery. This galactic giant is not just a collection of stars, gas, and dark matter, it is a storybook of the universe itself, containing chapters that span billions of years and countless transformations. The study of Andromeda has provided humanity with unparalleled insights into the life cycles of galaxies. Its close proximity makes it an ideal target for research, as we can observe its individual stars and clusters with remarkable clarity. Scientists have identified diverse stellar populations within Andromeda, each with unique characteristics and histories. From the bright, young blue stars of its spiral arms to the ancient, red stars in its halo, every stellar population tells a different part of the galaxy's story. These stars are not just cosmic objects, they are timekeepers, offering clues about the conditions that shaped Andromeda over its lifetime. Andromeda's history is written in the light of its stars, but it is also etched in the faint streams of material that surround it. These tidal streams are the remnants of smaller galaxies that were torn apart and absorbed by Andromeda's gravity. By mapping these streams, astronomers can reconstruct the galaxy's dynamic past, piecing together the cosmic interactions that have shaped its structure. Each stream represents a merger, a collision, or a gravitational tug-of-war that occurred millions or even billions of years ago. Together, they form a mosaic of Andromeda's evolutionary journey, providing a glimpse into the violent processes that drive galactic growth. The role of dark matter in Andromeda's formation and evolution cannot be overstated. This invisible, enigmatic substance makes up the majority of the galaxy's mass, yet its true nature remains one of the greatest unsolved mysteries in modern science. Dark matter does not emit or absorb light, making it undetectable through conventional means. However, its presence is inferred from its gravitational effects on visible matter. In Andromeda, dark matter forms an extensive halo that stretches far beyond the galaxy's luminous disk, influencing the motion of its stars and satellite galaxies. By studying the distribution and behavior of dark matter in Andromeda, scientists hope to unlock clues about the fundamental composition of the universe itself. Andromeda's future is as fascinating as its past. The impending collision with the Milky Way is not just an event of local significance, it is a cosmic spectacle that will reshape the local group of galaxies. This merger will occur over billions of years, beginning with subtle gravitational interactions that will distort the shapes of both galaxies. As the two spiral galaxies draw closer, their stars will form tidal bridges, connecting the two systems in a gravitational embrace. Gas clouds will collide, triggering bursts of star formation and creating brilliant nebulae that will light up the night skies of any planets within these galaxies. Eventually, the two galaxies will merge into a single, massive elliptical galaxy, a testament to the transformative power of gravity on cosmic scales. While the prospect of this collision may seem daunting, it is a reminder of the dynamic and ever-changing nature of the universe. Galaxies are not static islands of stars, they are constantly interacting, merging, and evolving. The Andromeda-Milky Way collision will not only reshape the structure of these galaxies but also provide a unique opportunity to study the processes that drive galactic evolution. For astronomers billions of years in the future, this event will be a natural laboratory for understanding the interplay of gravity, dark matter, and interstellar gas. The Andromeda Galaxy has also inspired humanity to think beyond our own cosmic neighborhood. The possibility of life in Andromeda, while purely speculative, raises profound questions about the nature of the universe and our place within it. If planets orbit stars in Andromeda, and there is no reason to believe they do not, then the potential for life beyond the Milky Way becomes a tantalizing prospect. While the vast distances between galaxies make direct exploration unlikely for the foreseeable future, the study of Andromeda fuels our imagination and drives the development of new technologies that may one day bring us closer to answering these profound questions. Telescopes have played a crucial role in our understanding of Andromeda, transforming it from a faint smudge in the night sky to one of the most studied objects in the universe. Ground-based observatories equipped with advanced adaptive optics systems have provided detailed views of the galaxy's structure, while space-based telescopes like Hubble have captured breathtaking images that reveal its intricate beauty. These observations have not only deepened our understanding of Andromeda but also served as a benchmark for studying other galaxies. By comparing Andromeda to galaxies at various distances, astronomers can piece together a timeline of cosmic history, tracing the evolution of galaxies from the early universe to the present day. Andromeda's spiral arms, central bulge, and halo are all areas of active research, each offering unique insights into the workings of galaxies. The spiral arms are regions of intense star formation, where massive stars light up the surrounding gas and dust, creating some of the most beautiful and dynamic regions in the galaxy. The central bulge, by contrast, is dominated by older stars, providing a window into the galaxy's past. The halo, with its sparse population of ancient stars and globular clusters, represents the remnants of Andromeda's earliest epochs, a fossil record of the galaxy's formation and growth. As we continue to study Andromeda, we are reminded of the interconnectedness of all things in the universe. The same processes that shape this distant galaxy are at work in the Milky Way and countless other galaxies. By studying Andromeda, we gain a deeper understanding of our own galaxy, our place in the cosmos, and the forces that govern the universe. The Andromeda Galaxy stands as a pillar of scientific curiosity and inquiry, revealing profound truths about the universe's structure and evolution. Each observation, each analysis of this celestial neighbor deepens our understanding of the intricate forces that shape galaxies, including our own Milky Way. Scientists and astronomers have spent decades unraveling its mysteries, from its unique physical characteristics to the secrets hidden in its dark matter halo, which stretches far beyond its visible edges. To expand the horizon of understanding Andromeda, we delve even deeper into the vast scientific details that define this monumental galaxy. One of the key features of Andromeda is its massive dark matter halo, a structure so vast and diffuse that it dominates the dynamics of the galaxy. Observations suggest that this halo extends hundreds of thousands of light-years beyond the galaxy's luminous disk, encompassing both its satellite galaxies and intergalactic space. Unlike the stars and gas within the galaxy, dark matter does not interact with electromagnetic forces, making it invisible to telescopes. However, its gravitational effects are profound. The motion of stars in Andromeda's outer regions can only be explained if we account for the gravitational influence of this unseen mass. The study of Andromeda's dark matter halo has significant implications for cosmology. By measuring its distribution and density, astronomers can test theories about the formation of large-scale structures in the universe. The presence of such a massive halo supports the lambda-CDM, lambda-cold dark matter, model, which posits that galaxies form within vast, invisible scaffolds of dark matter. Furthermore, detailed mapping of Andromeda's halo through gravitational lensing and stellar dynamics provides clues about the nature of dark matter particles, one of the most elusive questions in modern physics. Another remarkable aspect of Andromeda is its double nucleus, a feature that has fascinated scientists since its discovery. This central region contains two distinct clusters of stars, separated by only a few light-years. The prevailing hypothesis is that one of these clusters represents a dense group of stars surrounding Andromeda's supermassive black hole, while the other is a remnant of a smaller galaxy that merged with Andromeda long ago. This unusual configuration offers a unique opportunity to study the dynamics of galactic nuclei and the behavior of stars in extreme gravitational environments. The supermassive black hole at the center of Andromeda is estimated to be about 140 million times the mass of the Sun, significantly larger than the black hole at the center of the Milky Way. This immense gravitational powerhouse shapes the orbits of stars within the galaxy's central bulge and influences the flow of interstellar gas. Observing the interactions between this black hole and its surroundings provides critical data for understanding the growth and evolution of supermassive black holes across the universe. These observations also help astronomers explore the relationship between black holes and their host galaxies, a fundamental question in astrophysics. Andromeda's satellite galaxies add another layer of complexity to its story. These smaller galaxies, such as M32 and M110, orbit Andromeda in intricate patterns, influenced by its massive gravitational pull. Some of these satellites are in the process of being torn apart, their stars and gas streams forming tidal tails that arc across the sky. These interactions offer a glimpse into the hierarchical nature of galaxy formation, where larger systems grow by accreting smaller ones. By studying these satellites and their interactions with Andromeda, scientists can reconstruct the galaxy's merger history, tracing its growth over billions of years. The star-forming regions within Andromeda are particularly noteworthy for their scientific importance. These areas, known as HII regions, are dense clouds of ionized hydrogen where new stars are born. Observations of these regions provide valuable insights into the processes that govern star formation, such as the role of magnetic fields, turbulence, and feedback from massive stars. The distribution and intensity of star-forming regions within Andromeda's spiral arms also shed light on the dynamics of spiral galaxies, revealing how density waves and gravitational interactions shape their structure. Andromeda's globular clusters, ancient spherical collections of stars, are another key area of research. These clusters, which orbit the galaxy in its halo, are among the oldest objects in the universe, with ages exceeding 10 billion years. By studying the chemical composition and motion of these clusters, astronomers can infer the conditions that prevailed in the early universe when Andromeda was forming. Some globular clusters in Andromeda are thought to have originated in smaller galaxies that were later absorbed by the larger system, providing further evidence of its dynamic and turbulent history. One of the most exciting fields of research involving Andromeda is the search for exoplanets within its borders. While detecting planets in another galaxy is extraordinarily challenging, advancements in observational techniques have made this possibility increasingly feasible. For example, gravitational microlensing, a phenomenon where a massive object bends and magnifies the light of a more distant star, can be used to detect planets in Andromeda. If successful, these efforts could reveal the first evidence of planetary systems beyond the Milky Way, offering a new frontier for the study of exoplanets and the potential for life elsewhere in the universe. The impending collision between Andromeda and the Milky Way is one of the most significant events in the galaxy's future. As the two galaxies approach each other, their gravitational interactions will initiate a complex series of events that will reshape both systems. Gas clouds will collide, triggering bursts of star formation that will light up the night sky. Spiral arms will be torn apart, forming tidal streams and bridges of stars. Over billions of years, the two galaxies will merge into a single, massive elliptical galaxy. Simulations of this process provide a detailed look at how such mergers unfold, offering a unique perspective on the long-term evolution of galaxies. The study of Andromeda extends beyond the visible spectrum. Observations in infrared, ultraviolet, and X-ray wavelengths have revealed phenomena that are invisible to the human eye. Infrared studies, for example, penetrate the dust clouds within Andromeda, uncovering regions of intense star formation and the distribution of cooler stars. Ultraviolet observations highlight the youngest and hottest stars, while X-ray studies detect high-energy processes near the galaxy's supermassive black hole and in its dynamic star-forming regions. Together, these observations provide a multi-wavelength view of Andromeda, allowing astronomers to build a comprehensive picture of its structure and activity. Andromeda continues to inspire not only scientists but also the broader public, serving as a symbol of humanity's quest to explore and understand the universe. Its presence in the night sky, visible as a faint smudge to the naked eye, connects us to the vastness of the cosmos and reminds us of our place within it. Through telescopes and spacecraft, we have transformed this distant neighbor from an object of curiosity into a cornerstone of modern astrophysics, a testament to the power of human ingenuity and imagination. The Andromeda Galaxy is more than just a spiral of stars, gas, and dust. It is a dynamic system governed by complex physical processes that stretch the boundaries of our understanding. Each layer of Andromeda, from its luminous core to its diffuse halo, offers a wealth of information about the forces shaping galaxies, the origins of the universe, and the interconnected nature of cosmic structures. To truly appreciate the depth of Andromeda's scientific significance, we must dive further into its intricate details, probing the mechanisms that govern its past, present, and future. One of the most intriguing phenomena in Andromeda is the ongoing interaction between its stars and interstellar medium, ISM. The ISM is a mixture of gas, dust, and plasma that permeates the galaxy, acting as the raw material for star formation. Andromeda's ISM is highly structured, forming filamentary clouds, dense clumps, and expansive regions of ionized gas. Observations of the ISM reveal the complex interplay between gravity, magnetic fields, and feedback from stellar winds and supernovae. These processes regulate the galaxy's star formation rate, determining how efficiently Andromeda converts gas into stars over time. Star formation within Andromeda is not uniform, it is concentrated in specific regions, particularly along the spiral arms. These arms are sites of enhanced density, where shock waves from density waves compress gas clouds, triggering gravitational collapse. The role of density waves in spiral galaxies like Andromeda has been a subject of extensive study, as they provide a framework for understanding the long-lived spiral patterns observed in galaxies. These waves are essentially gravitational oscillations that propagate through the disk of the galaxy, concentrating stars and gas into spiral patterns without the material itself permanently remaining in the arms. This dynamic structure ensures a steady cycle of star formation and dispersal. The star formation process itself is driven by a delicate balance of forces. Gravity works to collapse gas clouds, forming protostars, while thermal pressure, turbulence, and magnetic fields resist collapse. In Andromeda, regions of active star formation are often accompanied by intense feedback from massive stars. These stars emit powerful ultraviolet radiation, which ionizes the surrounding gas, creating glowing nebulae known as HII regions. As these stars reach the end of their lives, they explode as supernovae, releasing vast amounts of energy and enriching the ISM with heavy elements. This enrichment is a critical step in the chemical evolution of galaxies, as it provides the building blocks for planets and life. The chemical composition of Andromeda's stars and ISM offers insights into its history of star formation and mergers. Spectroscopic studies reveal a gradient in metallicity, the abundance of elements heavier than hydrogen and helium, across the galaxy. The central bulge, which contains older stars, has a higher metallicity, reflecting a history of intense star formation in the galaxy's early years. In contrast, the outer regions of the disk and halo have lower metallicity, suggesting a slower rate of chemical enrichment. This gradient is a fingerprint of the processes that have shaped Andromeda over billions of years, from its initial collapse to its interactions with other galaxies. Andromeda's globular clusters are another rich source of information about its chemical and dynamical history. These dense collections of stars are among the oldest objects in the galaxy, with ages often exceeding 10 billion years. By studying the motions and compositions of these clusters, astronomers can reconstruct the conditions that prevailed when Andromeda was forming. Some globular clusters exhibit unusual properties, such as retrograde orbits or distinct chemical signatures, suggesting that they originated in smaller galaxies that were later accreted by Andromeda. These findings support the hierarchical model of galaxy formation, in which large galaxies grow through the assimilation of smaller systems. Beyond its visible components, Andromeda's structure is profoundly influenced by its dark matter halo. This halo, which extends far beyond the galaxy's disk, dominates its mass and shapes the motion of stars and satellite galaxies. By measuring the rotation curve of Andromeda, how the orbital speed of stars varies with distance from the center, astronomers have inferred the presence and distribution of dark matter. The flatness of the rotation curve at large distances, where visible matter becomes sparse, is a clear indication of the gravitational influence of dark matter. This discovery has been pivotal in the development of modern cosmology, highlighting the importance of unseen components in shaping the universe. The relationship between Andromeda and its satellite galaxies is another area of intense study. These smaller systems, such as M32, M110, and others, are bound to Andromeda by its gravitational pull, forming a miniature ecosystem within the local galaxy. Some of these satellites are in the process of being disrupted, their stars forming tidal streams that weave through Andromeda's halo. These streams provide a snapshot of galactic cannibalism in action, illustrating how large galaxies grow by accreting smaller ones. By mapping these streams, astronomers can reconstruct the orbits of the disrupted galaxies, revealing the history of their interactions with Andromeda. The study of Andromeda extends beyond its stars and dark matter to its population of supermassive black holes, neutron stars, and other exotic objects. The central black hole, with a mass of 140 million suns, is a key feature of the galaxy's core. This black hole influences the orbits of nearby stars and may play a role in regulating the flow of gas into the central regions. Observations of X-ray and radio emissions from the core provide clues about the activity of this black hole, which is currently in a relatively quiescent state. Future observations may reveal periods of increased activity, such as flares caused by the accretion of matter. Andromeda's neutron stars and stellar mass black holes are remnants of massive stars that have completed their life cycles. These objects are often found in binary systems, where they accrete matter from a companion star. As this matter falls onto the compact object, it releases energy in the form of X-rays, creating some of the brightest sources in the galaxy. Studying these systems in Andromeda provides insights into the end stages of stellar evolution and the dynamics of binary systems. The future of Andromeda is perhaps its most captivating aspect. Its collision with the Milky Way will mark a new chapter in the history of both galaxies, reshaping their structures and forming a new cosmic entity. Simulations of this merger reveal the complex interplay of gravitational forces, which will tear apart the spiral arms, create tidal bridges and streams, and trigger bursts of star formation. Over billions of years, the two galaxies will settle into a massive elliptical galaxy, a testament to the dynamic and interconnected nature of the cosmos. As we probe deeper into the Andromeda galaxy, it becomes increasingly clear that this celestial neighbor is not just an isolated system but a microcosm of the universe. Its intricate structure, dynamic interactions, and rich history make it a cornerstone of modern astrophysics, offering answers to some of the most profound questions about the nature of galaxies and the forces that govern the cosmos. The Andromeda Galaxy, our closest galactic neighbor, is not just a vast collection of stars, gas, and dark matter. It's a living laboratory where the secrets of the universe are constantly unfolding. Every corner of this colossal spiral galaxy, from its glittering core to its faint outer halo, holds stories of creation, destruction, and rebirth on a scale that challenges the limits of human imagination. At the heart of Andromeda's mysteries lies a component we cannot see, dark matter. This enigmatic substance, which makes up most of the galaxy's mass, doesn't emit light, heat, or any detectable radiation. Instead, we infer its presence through its gravitational influence on the galaxy's stars and gas. Without dark matter, Andromeda's majestic spiral arms wouldn't hold together, they would have unraveled long ago. Dark matter forms a vast, invisible halo around Andromeda, extending hundreds of thousands of light-years beyond its visible disk. The gravity of this halo acts as scaffolding, pulling stars, gas, and dust into the familiar spiral structure we observe today. Mapping this halo is one of the most exciting challenges in astrophysics. Using gravitational lensing, a phenomenon where dark matter bends the light of background objects, astronomers are beginning to trace its contours, revealing a hidden architecture that underpins the galaxy. This work isn't just about understanding Andromeda. Dark matter halos like this exist around all galaxies, and by studying the closest example, we gain insight into the invisible framework that shaped the entire universe. Andromeda's core is unlike anything in the Milky Way. At its center lies not one, but two dense clusters of stars, a double nucleus. One cluster orbits a supermassive black hole that's 140 million times the mass of the Sun. The other, offset slightly, might be the remnants of a smaller galaxy swallowed by Andromeda in the distant past. Why does Andromeda have two nuclei? One hypothesis is that the second cluster is the cause of a galactic collision. Billions of years ago, Andromeda likely devoured a smaller galaxy, and its core didn't disintegrate entirely. It became trapped, orbiting within Andromeda's gravitational well. Over time, the orbits of these two clusters will likely merge, adding to the already extraordinary mass of the central black hole. Andromeda's spiral arms are bustling regions of activity where stars are born. These arms are shaped by waves of density, essentially gravitational traffic jams. As gas clouds enter these high-density regions, they slow down, compress, and ignite in bursts of star formation. Massive blue stars, some tens of times the mass of the Sun, dominate these regions, shining brightly but living short, fiery lives before exploding as supernovae. These explosions are cosmic recycling events. They scatter heavy elements, like carbon, oxygen, and hydrogen, into the surrounding space, enriching the galaxy's interstellar medium. Without these elements, planets like Earth and life as we know it couldn't exist.
We no longer have
In a
control of the
way,
situation.
Andromeda's
Fall
star-forming regions are factories producing the raw materials for future worlds. Beyond its bright core and spiral arms lies Andromeda's halo, a dim, extended region filled with ancient stars and faint remnants of past collisions. This halo is a treasure trove for galactic archaeologists, astronomers who reconstruct the history of galaxies by studying their structures and stellar populations. One of the most fascinating features in Andromeda's halo is its stellar streams, long, faint trails of stars left behind by smaller galaxies that Andromeda has absorbed over billions of years. These streams are cosmic fossils, preserving the memory of galactic mergers. By mapping these trails, astronomers can recreate Andromeda's growth history, revealing a violent past of collisions and cannibalism. The largest and most famous of these streams is the giant stellar stream, a 100,000 light-year-long ribbon of stars thought to be the remains of a once massive satellite galaxy. Studying these structures helps scientists understand not just Andromeda's history, but also how galaxies like the Milky Way grow through mergers and accretion. Perhaps the most dramatic chapter in Andromeda's story is yet to come. Observations show that Andromeda is hurtling toward the Milky Way at a speed of 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide at a concentration that will reshape the local group of galaxies forever. What will happen during this collision? As the galaxies approach, their gravitational forces will pull at each other, distorting their shapes and flinging stars into long tidal tails. Gas clouds will collide, sparking bursts of star formation on an unprecedented scale. Over time, the two galaxies will merge into a single, massive elliptical galaxy, often nicknamed Milkomeda. Despite the scale of this event, individual stars are unlikely to collide due to the vast distances between them. Instead, the collision will create a spectacular light show, with new stars igniting and tidal streams painting the night sky. Andromeda's stars likely host countless planets, yet we've only just begun to explore this possibility. Detecting planets in another galaxy is an extraordinary challenge, but emerging techniques like gravitational microlensing are opening new doors. Microlensing occurs when a massive object passes in front of a background star, magnifying its light and revealing the presence of orbiting planets. If planets are found in Andromeda, they could be vastly different from those in the Milky Way, shaped by the unique environment of their galaxy. Some might orbit stars in dense clusters, experiencing a sky filled with thousands of brilliant suns. Others might lie in regions of relative isolation, circling stars on the edges of the galaxy's spiral arms. The discovery of exoplanets in Andromeda would not only expand our understanding of planetary systems but also ignite the imagination, reminding us of the potential for life beyond our galactic borders. The Andromeda Galaxy is more than a cosmic neighbor, it is a gateway to understanding the universe itself. Its proximity allows us to study phenomena that occur in distant galaxies but are too faint to observe in detail. By examining Andromeda's structure, star populations, and interactions, we gain a clearer picture of how galaxies form, evolve, and eventually meet their fate. Andromeda is a living reminder of the interconnectedness of the cosmos. Its stars, much like those in our Milky Way, are born, live, and die in cycles that produce the elements necessary for life. Its dark matter halo, mysterious and invisible, binds it together, just as dark matter structures the universe on the largest scales. As we look toward Andromeda with ever-advancing telescopes and instruments, We are not just observing another galaxy, we are peering into the mechanisms that govern the cosmos itself. And in its vastness, we are reminded of our small but significant place in this grand, unfolding story. The Andromeda Galaxy is a testament to the universe's complexity, a place where science converges with the unknown. Every new observation of its vast expanse reveals another piece of the puzzle about galactic evolution and the forces shaping the cosmos. The galaxy's massive disk contains over 1 trillion stars, a stellar population far larger than that of the Milky Way. Within this stellar population, we find stars in every stage of their life cycle, from bright, young blue stars to ancient red giants that serve as time capsules from an earlier universe. This mixture of stars offers a unique opportunity to study how galaxies grow and change over billions of years. The interplay between stars and their surrounding environment is evident in Andromeda's disk. Its regions of active star formation are lit up by massive, short-lived stars whose intense ultraviolet radiation ionizes nearby gas clouds, creating glowing nebulae. These regions are dynamic, constantly reshaped by the forces of stellar winds and supernova explosions. Such activity enriches the interstellar medium with heavier elements, providing the raw materials for the next generation of stars and planets. Beyond its spiral arms lies a much fainter halo of stars, globular clusters, and streams of debris from past galactic interactions. This halo, extending hundreds of thousands of light-years from the galaxy's center, is a goldmine for understanding Andromeda's violent history. Stellar streams, such as the giant stellar stream, are remnants of smaller galaxies that Andromeda absorbed, a process that continues to this day. These streams are faint and difficult to detect, but their existence provides critical evidence of the hierarchical nature of galaxy formation, where larger systems grow through the accretion of smaller ones. At the core of Andromeda lies its supermassive black hole, surrounded by a dense swarm of stars. This black hole, millions of times the mass of the Sun, is a region of intense gravitational forces. Stars in the vicinity of the black hole exhibit rapid orbital motions, a direct consequence of its immense mass. While currently in a relatively dormant state, this black hole has likely experienced periods of heightened activity, consuming nearby material and releasing enormous amounts of energy. Observing these central regions offers a glimpse into the processes that occur in galactic nuclei, phenomena that are common throughout the universe but challenging to observe in distant galaxies. Andromeda's double nucleus adds another layer of intrigue to its central region. This dual structure, consisting of two closely separated clusters of stars, suggests a complex history of mergers and interactions. One hypothesis is that this feature represents the remnants of a smaller galaxy's core, trapped in Andromeda's gravitational field after a past collision. Such findings illustrate the dynamic and ever-changing nature of galaxies, where interactions with neighbors leave lasting imprints on their structure. As we move outward from the core, the galaxy's spiral arms showcase the intricate patterns formed by density waves. These arms are not static structures but rather regions of increased density that rotate through the galaxy, compressing gas clouds and triggering star formation as they move. The arms' composition, a mix of bright young stars and dark interstellar dust, highlights the ongoing processes that sustain the galaxy's activity. Andromeda's relationship with its satellite galaxies further enriches its story. These smaller companions, such as M32 and M110, orbit within its gravitational influence, and some are being actively disrupted. Tidal forces exerted by Andromeda pull stars and gas from these satellites, adding to the galaxy's mass and leaving behind streams of debris. Observing these interactions helps astronomers understand how galaxies grow over time and how smaller systems contribute to the evolution of larger ones. The dark matter halo surrounding Andromeda is a dominant feature of its structure, extending far beyond its visible components. This halo, made of unseen material, accounts for the majority of the galaxy's mass. Its gravitational influence shapes the orbits of stars and satellite galaxies and plays a crucial role in maintaining the stability of the spiral arms. Mapping the distribution of dark matter in Andromeda provides a critical test for theories about the nature of this mysterious substance and its role in the formation of large-scale cosmic structures. Andromeda's impending collision with the Milky Way is one of the most dramatic events in its future. As the two galaxies approach each other, their mutual gravitational pull will distort their shapes, creating tidal tails and bridges of stars. Gas clouds from both galaxies will collide, igniting bursts of star formation that will illuminate the night skies. Over billions of years, the two systems will merge, forming a massive elliptical galaxy. While such an event might seem catastrophic, the vast distances between individual stars mean that direct collisions are unlikely. Instead, the merger will result in a profound reshaping of both galaxies, a process that has occurred countless times throughout the universe's history. The study of Andromeda extends beyond visible light, with observations across the electromagnetic spectrum providing a more complete picture of its structure and activity. Infrared observations penetrate the dust in its spiral arms, revealing regions of active star formation. Ultraviolet light highlights young, massive stars, while X-ray emissions point to high-energy processes near the supermassive black hole and within binary star systems. Each wavelength reveals a different aspect of the galaxy, contributing to a comprehensive understanding of its nature. Andromeda's role in the local group of galaxies extends beyond its interactions with the Milky Way and its satellites. As the largest galaxy in this group, it exerts a significant gravitational influence, shaping the motions of neighboring galaxies. These interactions provide a scaled-down model of the processes that occur in larger galaxy clusters, where gravitational forces and mergers dominate the dynamics of the system. Studying Andromeda also offers a window into the conditions necessary for the formation of habitable planets and the potential for life beyond the Milky Way. While direct detection of exoplanets in Andromeda is not yet possible, the principles of planetary formation suggest that its stars likely host a diverse array of planets. If life exists elsewhere in the universe, studying nearby galaxies like Andromeda helps us understand the environments where it might thrive. The Andromeda Galaxy, in its immense complexity and dynamic nature, stands as a microcosm of the universe itself. Its stars, gas, dark matter, and interactions with neighboring systems embody the forces that shape galaxies on all scales. As technology advances, our ability to study Andromeda will only deepen, offering new insights into the workings of the cosmos and our place within it. Each discovery within Andromeda's borders reminds us of the intricate and interconnected nature of the universe, a tapestry woven from countless interactions over billions of years. The Andromeda Galaxy's complexity extends into every observable component, providing endless avenues for scientific discovery. Its stars, spanning a wide range of ages and compositions, form the backbone of its luminous structure. By examining the light emitted by these stars, astronomers have gained a detailed understanding of their chemical abundances, ages, and distribution throughout the galaxy. These stellar populations are grouped into distinct categories, the young, massive stars in the spiral arms, the older, metal-rich stars in the bulge, and the ancient, metal-poor stars in the halo. Each group tells a different chapter of Andromeda's history, revealing how the galaxy grew and evolved over cosmic time. The young stars in Andromeda's disk are concentrated in its spiral arms, where conditions are ideal for star formation. These regions are shaped by density waves, which compress gas clouds as they travel through the disk. This compression triggers gravitational collapse, leading to the birth of new stars. Observing these regions allows scientists to study the initial stages of stellar evolution, from protostars to fully formed stars. The increased radiation from young, massive stars heats the surrounding gas, creating ionized bubbles that emit light across the electromagnetic spectrum. The older stars in Andromeda's bulge, by contrast, are remnants of the galaxy's early history. These stars formed during a period of intense star formation that occurred billions of years ago, likely fueled by the inflow of gas from the early universe. The bulge's stars are densely packed, orbiting the galaxy's center in a complex gravitational dance. Their chemical composition reflects the conditions of the early universe, providing a glimpse into the processes that enriched the interstellar medium with heavy elements. Andromeda's halo contains some of the oldest stars in the galaxy, as well as a population of globular clusters that date back to its formation. These clusters, which contain hundreds of thousands of stars, are relics of the early universe, surviving relatively unchanged over billions of years. The motion and composition of these clusters offer clues about Andromeda's formation, suggesting that many of them originated in smaller galaxies that were later absorbed. Studying these ancient structures helps scientists understand the earliest stages of galaxy formation, a process that began less than 1 billion years after the Big Bang. The halo is also home to Andromeda's faintest and most elusive components, its stellar streams. These streams are the remnants of smaller galaxies that Andromeda captured and disrupted through gravitational interactions. By mapping the distribution of these streams, astronomers can reconstruct the galaxy's merger history, revealing a timeline of interactions that shaped its current structure. These streams are not static, they evolve over time, mixing with Andromeda's halo and contributing to its overall mass. Andromeda's dark matter halo, though invisible, is one of its most significant features. This vast, diffuse structure extends far beyond the visible galaxy, accounting for most of its mass. Without the gravitational pull of dark matter, Andromeda's stars and gas would not remain bound, and its spiral structure would not persist. The presence of dark matter is inferred from the galaxy's rotation curve, which remains flat even at great distances from the center. This behavior is inconsistent with the amount of visible matter alone, pointing to the dominance of an unseen component. The nature of dark matter remains one of the greatest mysteries in physics. Observing Andromeda's halo offers a unique opportunity to study this enigmatic substance, as its proximity allows for detailed measurements of its gravitational effects. By combining data from Andromeda with observations of other galaxies and galaxy clusters, scientists hope to constrain the properties of dark matter and understand its role in shaping the universe. Andromeda's relationship with its satellite galaxies adds another layer of complexity to its story. These smaller systems, numbering more than 20, orbit Andromeda within its dark matter halo. Some, like M32 and M110, are easily visible, while others are faint and difficult to detect. These satellites are subject to tidal forces that can strip away their stars and gas, adding to Andromeda's mass and forming tidal streams. The
The
ongoing interactions between Andromeda and its satellites provide a real-time example of hierarchical galaxy formation, a process that has occurred throughout the universe. The impending collision between Andromeda and the Milky Way will mark a transformative event in the local group of galaxies. This merger, set to occur in about 4.5 billion years, will create a new, massive galaxy that combines the stars, gas, and dark matter of both systems. Simulations of this event predict a dramatic reshaping of both galaxies, with their spiral structures destroyed and replaced by a more spheroidal configuration. This process will also redistribute their dark matter halos, creating a new gravitational equilibrium. During the collision, gas clouds from both galaxies will collide and compress, triggering bursts of star formation. These events, known as starbursts, will illuminate the newly forming galaxy, creating regions of intense brightness. At the same time, the supermassive black holes at the centers of Andromeda and the Milky Way may merge, releasing enormous amounts of energy in the form of gravitational waves. These waves, ripples in spacetime, will propagate outward, carrying information about the black hole's masses and spin. While the Andromeda-Milky Way collision is often described as a cataclysmic event, the vast distances between stars mean that direct stellar collisions are unlikely. Instead, the merger will reshape the orbits of stars and gas, creating new tidal structures and redistributing material throughout the galaxy. Over billions of years, the two galaxies will settle into a stable configuration, forming an elliptical galaxy that astronomers have dubbed Mokomata. The study of Andromeda extends across the electromagnetic spectrum, with observations in ultraviolet, infrared, and X-ray wavelengths providing a more complete picture of its structure and activity. Ultraviolet light reveals the youngest, hottest stars in the galaxy, while infrared observations penetrate dust clouds to uncover regions of active star formation. X-ray emissions, on the other hand, highlight high-energy processes near Andromeda's supermassive black hole and within its population of neutron stars and stellar mass black holes. The wealth of data collected from Andromeda has implications far beyond the local group. By studying its structure, dynamics, and composition, astronomers can test theories of galaxy formation and evolution that apply across the universe. Andromeda serves as a laboratory for understanding the processes that govern galaxies at all scales, from the smallest dwarfs to the largest clusters. The Andromeda Galaxy, in its vastness and complexity, embodies the interconnected nature of the universe. Each of its components, from the stars in its disk to the dark matter in its halo, plays a role in shaping its structure and behavior. As our understanding of Andromeda deepens, so too does our appreciation for the forces that govern the cosmos. It stands as a reminder of the universe's boundless potential for discovery, a cosmic neighbor whose secrets continue to inspire and challenge our understanding of the universe. The Andromeda Galaxy is not merely a subject of awe-inspiring beauty, it is a cornerstone of astrophysical research, a galaxy so close that it offers a detailed view into processes that govern the universe at large. With every new generation of instruments and theoretical models, Andromeda becomes an even more potent laboratory for exploring the physics of galaxies, the nature of dark matter, and the history of the cosmos. A significant aspect of ongoing research into Andromeda involves its rotational dynamics. The galaxy's rotation curve, a plot showing how the orbital velocity of stars changes with distance from the center, provides one of the most compelling pieces of evidence for the existence of dark matter. Unlike what would be expected if only visible matter were present, the rotation curve of Andromeda remains nearly flat at large distances from its core, even where the visible mass is negligible. This indicates the presence of an unseen halo of dark matter extending far beyond the luminous disk. By comparing the rotation curves of Andromeda with those of other galaxies, astronomers can refine models of dark matter distribution and its influence on galactic structure. In addition to dark matter, studies of Andromeda's stellar populations are unlocking secrets about galaxy formation and evolution. Detailed spectroscopic surveys, such as those conducted with the Keck Observatory and the Hubble Space Telescope, have allowed scientists to determine the metallicity of stars in different regions of the galaxy. Metallicity, the proportion of elements heavier than hydrogen and helium, acts as a cosmic clock, revealing the star formation history of the galaxy. The high metallicity of stars in Andromeda's central bulge reflects an early period of rapid star formation, likely driven by the inflow of gas and the intense gravitational dynamics of its core. In contrast, the outer regions of the disk and halo contain stars with lower metallicities, indicating slower chemical enrichment over time. These metallicity gradients are critical for understanding not only Andromeda but also galaxy evolution on a universal scale. For instance, the presence of metal-poor stars in Andromeda's halo suggests that these stars are remnants of smaller galaxies that merged with Andromeda in the past. This supports the hierarchical model of galaxy formation, in which large galaxies grow through the accretion of smaller ones. By studying the ages, compositions, and motions of these stars, astronomers can reconstruct the timeline of Andromeda's mergers and interactions, painting a picture of its growth over billions of years. One of the most fascinating discoveries in recent years has been the identification of tidal streams in Andromeda's halo. These faint, elongated structures are the remnants of dwarf galaxies torn apart by Andromeda's gravitational pull. Among the most prominent is the giant stellar stream, a structure spanning over 100,000 light-years, thought to be the remains of a galaxy that collided with Andromeda about 2 billion years ago. By mapping these streams with high-precision instruments, such as the Gaia Space Observatory, scientists can probe the gravitational potential of Andromeda's halo, providing insights into the distribution of dark matter and the galaxy's dynamic history. Beyond its stars and dark matter, Andromeda's interstellar medium, ISM, is a subject of intense study. The ISM, consisting of gas, dust, and cosmic rays, plays a crucial role in the life cycle of galaxies by serving as the reservoir for star formation. Observations in multiple wavelengths, including radio, infrared, and submillimeter, have revealed complex structures within Andromeda's ISM, from dense molecular clouds to diffuse atomic hydrogen regions. These structures are shaped by the interplay of gravitational forces, turbulence, magnetic fields, and feedback from massive stars and supernovae. The role of magnetic fields in shaping Andromeda's ISM is an emerging area of research. Using instruments such as the Very Large Array and the Atacama Large Millimeter/Submillimeter Array, astronomers are mapping the galaxy's magnetic field structure. These fields influence the motion of charged particles in the ISM, affecting star formation and the dynamics of gas flows. Understanding the strength and orientation of magnetic fields in Andromeda provides a deeper understanding of how galaxies regulate star formation and maintain their structure over time. Andromeda's satellite galaxies add another layer of complexity to its ecosystem. With over 20 known satellites, Andromeda serves as a microcosm for studying the dynamics of galaxy groups. Some satellites, like M32, show evidence of tidal stripping, where gravitational interactions with Andromeda have removed stars and gas, leaving behind a compact remnant. Others, like M110, are actively interacting with Andromeda, contributing material to its halo. These interactions provide a living example of galaxy evolution in action, offering a detailed view of processes that occur across the universe. The future merger between Andromeda and the Milky Way is one of the most anticipated cosmic events in the local universe. Current simulations of this event, such as those conducted with supercomputers using the Illustris and Eagle cosmological models, predict a series of dramatic transformations. As the galaxies approach, their gravitational interactions will distort their shapes, creating tidal tails and bridges of stars and gas. These features, reminiscent of structures seen in interacting galaxies like the antennae galaxies, provide a preview of what might unfold. The collision will ignite bursts of star formation, driven by the compression of gas as the galaxies merge. Over time, their central black holes will coalesce, emitting gravitational waves detectable by next-generation observatories such as the Laser Interferometer Space Antenna (LISA). Even as we anticipate this distant future, Andromeda remains a critical subject for understanding galaxy clusters beyond the local group. Its role as the largest member of our local group offers a scaled-down model of the processes occurring in massive galaxy clusters, where interactions between dark matter halos, gas dynamics, and star formation play out on a grander scale. By studying Andromeda, scientists refine the tools and theories that apply to systems billions of light-years away. Andromeda's study is also pushing the boundaries of exoplanet science. While detecting planets in another galaxy remains a challenge, methods such as gravitational microlensing and spectroscopy hold promise for identifying planets within Andromeda. Detecting such planets would open a new frontier in the search for extraterrestrial life, providing the first opportunity to study worlds beyond the Milky Way. If Andromeda's planetary systems resemble those of the Milky Way, it is likely teeming with diverse planets, some potentially orbiting within habitable zones where conditions might support life. As new telescopes come online, including the Extremely Large Telescope and the James Webb Space Telescope, Andromeda's secrets will continue to be unveiled. These instruments will provide unparalleled resolution and sensitivity, allowing astronomers to study individual stars and planetary systems within Andromeda, as well as its faintest tidal streams and most diffuse dark matter structures. Andromeda, as a living archive of cosmic history, will remain a focal point for unraveling the universe's grandest mysteries, inspiring generations of researchers and dreamers alike. The Andromeda Galaxy, as a living archive of cosmic evolution, continues to captivate the scientific community. With its immense size and proximity, it serves as an unparalleled laboratory for testing theories of galactic dynamics, star formation, and the nature of dark matter. As observational tools improve, researchers uncover increasingly intricate details about the processes that shape this massive spiral galaxy and its surrounding environment. One of the most active areas of research focuses on the interplay between Andromeda's interstellar medium, ISM, and star formation. The ISM is not a uniform structure, it consists of diverse phases, from cold molecular clouds to hot, ionized regions. Molecular clouds, composed primarily of molecular hydrogen, H2, are the birthplace of stars. Observations using radio telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, reveal these dense clouds in extraordinary detail. By studying their composition, density, and temperature, scientists gain insights into the conditions that lead to star formation. In Andromeda, these clouds are predominantly located along its spiral arms, where the compression of gas by density waves provides the necessary triggers for gravitational collapse. The role of feedback mechanisms in regulating star formation is another critical aspect of Andromeda's evolution. Massive stars, once formed, exert powerful feedback on their surroundings through stellar winds, ultraviolet radiation, and, ultimately, supernova explosions. These feedback processes inject energy into the ISM, heating it and dispersing gas, which can either suppress or stimulate further star formation. In Andromeda, feedback is visible throughout its disk, offering a dynamic view of the cyclical nature of star formation. Andromeda's spiral arms, while appearing as fixed features, are in constant motion. They are formed and sustained by density waves, which propagate through the galactic disk, concentrating stars and gas into patterns that resemble a spiral. These waves are not made of physical material but are rather regions of higher gravitational density that travel through the galaxy. Observing these arms in Andromeda has helped refine our understanding of how such structures form and persist in spiral galaxies across the universe. The distribution of stars and gas within these arms also provides clues about the interplay between galactic rotation, gravity, and star formation. The central bulge of Andromeda presents a stark contrast to its active spiral arms. This region, dominated by older, redder stars, is relatively quiescent, with little ongoing star formation. The stars in the bulge orbit in complex patterns, influenced by the galaxy's supermassive black hole and the dense gravitational environment of the central region. By studying the motion of these stars using spectroscopy, astronomers can map the distribution of mass in the bulge, including the unseen mass of the black hole and dark matter. These studies reveal that Andromeda's supermassive black hole, with a mass of approximately 140 million suns, is significantly larger than the one at the center of the Milky Way, suggesting differences in the growth histories of the two galaxies. The double nucleus of Andromeda, a rare and fascinating feature, continues to be a subject of intense investigation. Detailed observations suggest that this structure may result from the accretion of a smaller galaxy, whose core became embedded in Andromeda's central region. This scenario is supported by the presence of distinct stellar populations within the double nucleus, indicating different origins. This finding highlights the dynamic and often violent history of galaxy interactions and mergers that have shaped Andromeda into its current form. Andromeda's extensive halo, stretching far beyond its visible disk, is another area rich with scientific interest. This halo contains a mix of stars, globular clusters, and streams of debris from past mergers. Observations using the Hubble Space Telescope have revealed that Andromeda's halo is significantly more massive and extended than previously thought, providing crucial data about the distribution of dark matter. The halo also contains metal-poor stars, some of the oldest in the galaxy, which are remnants from the earliest phases of galactic formation. These stars serve as fossils, preserving information about the conditions in the universe when Andromeda was just beginning to form. The satellite galaxies of Andromeda, including M32, M110, and dozens of smaller dwarf galaxies, form a dynamic and interactive system. Some of these satellites are in the process of being disrupted by Andromeda's tidal forces, adding to the streams of stars in its halo. Others appear to be relatively stable, orbiting at distances where tidal forces are weaker. These satellites provide a microcosm for studying the hierarchical formation of galaxies, showing how smaller systems are absorbed by larger ones over time. They also serve as laboratories for understanding the role of dark matter in shaping the dynamics of small galaxies, as their visible mass is often insufficient to account for their observed motions. The impending collision between Andromeda and the Milky Way, while billions of years in the future, continues to be a focal point of theoretical studies and simulations. By modeling this event using powerful supercomputers, astronomers can predict the stages of the merger, from the initial gravitational interactions to the eventual formation of a single elliptical galaxy. These simulations incorporate data about the mass, composition, and motion of both galaxies, as well as their dark matter halos, to create highly detailed scenarios. The results provide insights not only into the future of our local group but also into the broader processes of galaxy evolution in the universe. In addition to its relevance for understanding large-scale cosmic structures, Andromeda is increasingly becoming a target for studies of exoplanetary systems. While direct detection of exoplanets in Andromeda remains beyond current technology, the principles of planetary formation suggest that many of its stars are likely to host planets. Observations of star-forming regions in Andromeda reveal conditions similar to those in the Milky Way, where planets are known to form around stars of various types. Future advancements in observational techniques, such as high-resolution spectroscopy and microlensing surveys, may allow astronomers to detect exoplanets within Andromeda, opening a new frontier in the search for habitable worlds beyond our galaxy. Andromeda's role as the largest galaxy in the local group also provides a unique perspective on the dynamics of galaxy clusters. Its interactions with the Milky Way and other members of the local group offer a scaled-down model of the processes that occur in much larger galaxy clusters, where gravitational forces and collisions dominate. By studying Andromeda, astronomers can test theories of cluster evolution, including the influence of dark energy on the expansion of the universe. Every aspect of Andromeda, from its smallest star-forming regions to its vast dark matter halo, contributes to our understanding of the universe. It is not merely a distant object in the sky but a dynamic, evolving system that embodies the processes shaping galaxies everywhere. As technology advances and observational techniques improve, Andromeda will continue to serve as a cornerstone of astrophysical research, inspiring new discoveries and expanding our knowledge of the cosmos. The Andromeda Galaxy continues to captivate not only astronomers but also the general public due to its role as both a scientific treasure trove and a cosmic marvel. Beyond its already well-documented features, there are countless other intriguing facets that expand our understanding of the universe and provoke even deeper questions about its nature. One particularly fascinating aspect of Andromeda is the ongoing discovery of ultra-diffuse galaxies, UDGs, within its vicinity. These faint, ghostly systems, scattered around Andromeda, are incredibly low in luminosity relative to their size. UDGs challenge our understanding of galaxy formation, as they are thought to contain large amounts of dark matter while having very few stars. Their existence raises questions about how galaxies form and survive in such extreme conditions. Observing these faint galaxies around Andromeda helps astronomers test models of dark matter and study how gravitational interactions with larger systems affect small, diffuse galaxies. Another intriguing topic is Andromeda's stellar remnants, white dwarfs, neutron stars, and black holes. These objects represent the end stages of stellar evolution and are crucial for understanding the life cycles of stars in Andromeda. By observing the X-rays emitted by binary systems where a neutron star or black hole accretes material from a companion star, astronomers can measure the mass, spin, and other properties of these exotic remnants. Such observations also provide clues about the population of high-mass stars that existed in Andromeda's past, as these stars eventually evolve into compact objects. The search for intermediate mass black holes, IMBHs, within Andromeda is an area of growing interest. IMBHs are thought to represent a missing link in the black hole population, bridging the gap between stellar mass black holes and supermassive black holes. Evidence for these elusive objects could come from dense star clusters in Andromeda's halo or from X-ray sources that exhibit peculiar properties. If confirmed, IMBHs could help explain how supermassive black holes like the one at Andromeda's center grow over time. The outer edges of Andromeda's disk and halo also hold surprises, such as extended ultraviolet, UV, disks discovered by the Galaxy Evolution Explorer, GALEX. These UV features suggest ongoing star formation in regions far beyond the visible disk of the galaxy. Such discoveries challenge traditional notions of where and how star formation occurs in spiral galaxies, hinting at the presence of low-density gas reservoirs that may slowly contribute to the galaxy's growth over billions of years. A lesser-discussed yet intriguing feature of Andromeda is its magnetic field. Magnetic fields are notoriously difficult to study, but they play a critical role in shaping the behavior of galaxies by influencing the motion of charged particles and the dynamics of the interstellar medium. Recent observations suggest that Andromeda's magnetic field is well-ordered, extending across its spiral arms and potentially contributing to the formation of dense molecular clouds. By mapping this magnetic field, scientists are beginning to uncover its role in regulating star formation and driving the flow of gas within the galaxy. In the realm of theoretical physics, Andromeda also provides a unique opportunity to test alternative theories of gravity. The behavior of stars in its halo, for instance, can be used to test modified Newtonian dynamics, MOND, or other theories that aim to explain galactic rotation curves without invoking dark matter. While dark matter remains the most widely accepted explanation, galaxies like Andromeda serve as critical testing grounds for alternative models, ensuring that our understanding of fundamental physics remains robust and open to new ideas. Andromeda's role in cosmology extends to its position within the local group, which itself is a microcosm of the larger cosmic web. The local group is dominated by Andromeda and the Milky Way, but it also includes smaller galaxies like the Triangulum Galaxy, M33, and numerous dwarfs. By studying the motion of these galaxies relative to Andromeda, astronomers gain insights into the gravitational interactions within galaxy groups. These interactions, in turn, reflect the distribution of dark matter on larger scales, helping to constrain cosmological models that describe the evolution of the universe from the Big Bang to the present day. On a more speculative note, Andromeda's potential for hosting habitable environments is a topic that sparks the imagination. While exoplanet research within the Milky Way has revealed thousands of planets, extending these studies to Andromeda could open new frontiers. Advanced methods, such as transit photometry or gravitational microlensing applied on an intergalactic scale, may one day allow the detection of planets orbiting stars in Andromeda. If such planets are found, their diversity could provide a broader context for understanding the conditions necessary for life. Furthermore, the discovery of biosignatures, chemical markers that indicate the presence of life, on planets in Andromeda would redefine humanity's place in the cosmos. The exploration of Andromeda is also fueling technological advancements. Instruments capable of resolving individual stars in Andromeda, such as those aboard the Hubble Space Telescope or the upcoming Extremely Large Telescope, ELT, push the boundaries of optical engineering. Similarly, the computational power required to simulate the future collision between Andromeda and the Milky Way drives innovation in numerical modeling and high-performance computing. These technologies not only deepen our understanding of Andromeda but also have broader applications in fields ranging from artificial intelligence to climate modeling. As humanity's knowledge of Andromeda grows, so does our appreciation of its role as a cornerstone of modern astrophysics. It is a galaxy that embodies the complexity, dynamism, and interconnectedness of the universe. Each new discovery, whether it involves the behavior of stars, the distribution of dark matter, or the interactions of satellite galaxies, adds to our understanding of the cosmos and our place within it. Andromeda stands as a symbol of both the mysteries that remain and the relentless pursuit of knowledge that defines humanity's exploration of the universe. The Andromeda Galaxy, vast and enigmatic, represents a bridge between the known and the unknown, between the observable universe and the mysteries that lie beyond. Its proximity provides humanity with an unparalleled opportunity to study a galaxy in extraordinary detail, serving as both a mirror and a map for understanding galaxies across the cosmos. Each star, each tidal stream, and each faint trace of dark matter within Andromeda tells a story, not just of its own formation, but of the fundamental processes that govern the universe. As we continue to probe Andromeda's secrets, we are reminded of the immense scale of the cosmos and our relatively small yet significant place within it. This galaxy, with its trillion stars and complex dynamics, invites us to think not only about the mechanisms that shape galaxies but also about the nature of existence itself. Its eventual collision with the Milky Way, an event of unimaginable scale, emphasizes the ever-changing, interconnected nature of the universe, where no galaxy exists in isolation. Andromeda is more than a neighbor, it is a cosmic partner in our journey of discovery. As our technology advances and our curiosity deepens, this majestic galaxy will continue to inspire not only scientific inquiry but also a profound sense of wonder. Through Andromeda, we glimpse the infinite possibilities of the cosmos, and in that glimpse, we find both questions to pursue and answers that redefine our understanding of the universe. It stands as a testament to the unending dance of matter, energy, and time, a galaxy that invites us to explore, imagine, and reach beyond. The Medusa Galaxy, also known as NGC 4194, is an intriguing and extraordinary cosmic structure located approximately 130 million light-years away in the constellation Ursa Major. It is classified as a merging galaxy, born from the collision of two previously independent galaxies, a process that has shaped its distinct and chaotic appearance. The Medusa moniker comes from the bright streamers of gas and stars that resemble the mythological character's snake-like hair, highlighting the dynamic processes at play in this galactic system. The Medusa system provides a wealth of scientific interest due to its rich interplay of stellar formation, gas dynamics, and the gravitational effects resulting from the galactic merger. The galactic collision that gave rise to the Jellyfish Galaxy is a prime example of how the universe is an ever-changing environment, driven by the relentless force of gravity. During this cataclysmic encounter, stars from the progenitor galaxies mostly passed by each other without colliding, as the distance between individual stars is vast on galactic scales. However, the massive clouds of gas within the two galaxies did interact, leading to intense bursts of star formation, a phenomenon astronomers refer to as a starburst. These starbursts are most visible in the core region of the structure, where dense molecular gas is compressed to form massive clusters of stars. Observing these starburst regions allows researchers to gain insight into the process of star formation under extreme conditions. The tangled morphology of the cosmic medusa is not limited to its starburst core. One of its most notable features is the extended tidal tail, a stream of stars and gas ejected into intergalactic space due to the gravitational forces during the merger. These tidal tails serve as a direct record of the interaction, helping astronomers reconstruct the history of the collision. The tail also contains young stars, whose formation was likely triggered by the compression of gas in these outlying regions. The study of such features provides a unique opportunity to explore the mechanisms behind galactic evolution and the role of interactions in shaping the universe's structure. The unique environment of this stellar hydra allows for the study of feedback processes, where newly formed stars influence their surroundings. Massive stars emit copious amounts of ultraviolet radiation and powerful stellar winds, which heat and ionize the surrounding gas. In extreme cases, supernova explosions from these stars further enrich the interstellar medium with heavy elements and drive gas outflows that can escape the galaxy's gravitational pull. Observing these processes in the medusa's environment helps scientists understand how galaxies regulate their growth and evolution over cosmic timescales. Furthermore, the chaotic nature of the nebular Gorgon is an ideal laboratory for studying the interstellar medium. The collision of the progenitor galaxies has created a turbulent and dynamic environment where gas exists in a wide range of temperatures and densities. Researchers can observe cold molecular gas, the raw material for star formation, as well as hot ionized gas that glows brightly in X-rays. The interactions between these phases of gas shed light on the complex physics that governs the interstellar medium and the role of turbulence in driving star formation. The study of the Serpentine galaxy extends beyond its immediate surroundings. Like other merging systems, it is believed that the Medusa will eventually evolve into a more stable elliptical galaxy, a process that takes billions of years. This transformation provides a glimpse into the future of galactic evolution and helps astronomers piece together the sequence of events that shape the observable universe. Additionally, merging systems like this one are thought to play a crucial role in the growth of supermassive black holes at the centers of galaxies. The Medusa galaxy's active core suggests the presence of such a black hole, which is likely accreting material from the surrounding gas, generating immense amounts of energy in the process. Advanced observational techniques have allowed astronomers to delve deeper into the anatomy of this galactic siren. Instruments aboard space telescopes like Hubble and Chandra, as well as ground-based observatories equipped with adaptive optics, have provided high-resolution images and spectral data of the system. These observations reveal not only the intricate structure of the galaxy but also the chemical composition of its stars and gas. By studying the elemental abundances in the Medusa's stars, researchers can trace the history of star formation and chemical enrichment, offering clues about the conditions in the universe during different epochs. In addition to its scientific significance, the radiant chimera serves as a visual testament to the beauty and complexity of the cosmos. Its vibrant colors, ranging from the deep red glow of hydrogen gas to the brilliant blue of young star clusters, offer a striking contrast that captivates astronomers and enthusiasts alike. These colors are not merely aesthetic, they provide valuable information about the physical processes within the galaxy. For instance, the red emission from hydrogen gas marks regions of active star formation, while the blue light from young stars indicates their relatively recent birth. The Medusa's story is not an isolated one. Galaxies like the stellar vortex are found throughout the universe, and their study contributes to our broader understanding of cosmic evolution. Collisions and mergers are common in the history of galaxies, including our own Milky Way, which is on a collision course with the Andromeda galaxy. By studying systems like the Medusa, scientists can predict the outcomes of such interactions and better understand the long-term evolution of galactic systems. The scientific investigation of the celestial hydra is an ongoing endeavor. As new telescopes and instruments are developed, astronomers will continue to unravel its mysteries, from the detailed mechanisms of star formation to the fate of its tidal tails. The insights gained from this galaxy and others like it are not just about understanding distant objects, they also shed light on the processes that have shaped our own cosmic neighborhood and the universe as a whole. The Medusa galaxy stands as a reminder of the dynamic and interconnected nature of the cosmos, a place where even the most chaotic and violent events give rise to beauty and new beginnings. The Medusa galaxy continues to provide an unparalleled perspective on the processes that govern the universe. Its chaotic structure, driven by the violent collision of two galaxies, acts as a cosmic laboratory where astronomers can observe the interplay of forces that shape galaxies over billions of years. The intricate dance of gravity, the dynamics of interstellar gas, and the cycle of star formation and destruction are all encapsulated within this remarkable system, making it a cornerstone for our understanding of cosmic evolution. One of the most striking aspects of the cosmic hydra is the diversity of star populations within it. The collision that created this galaxy triggered multiple waves of star formation, leading to the presence of stars of varying ages and metallicities. By analyzing the light emitted by these stars, astronomers can decipher the timeline of events that shaped the galaxy. Young, massive stars shine brightly in ultraviolet and blue light, while older, cooler stars emit red and infrared radiation. This combination of stellar populations allows researchers to reconstruct the galaxy's history and understand the long-term effects of galactic mergers. The tidal features of the nebular serpent are another area of intense scientific focus. These streams of stars and gas, stretching far beyond the main body of the galaxy, are evidence of the gravitational forces at work during the merger. Observations of these tidal tails have revealed that they are not uniform but contain clumps of gas and stars, suggesting localized regions of star formation. These star-forming clumps are of particular interest because they represent an environment vastly different from the dense cores of galaxies, providing a unique opportunity to study how stars form under low-density conditions. In addition to its visual and structural features, the Jellyfish galaxy is a hub of intense activity at other wavelengths of light. Infrared observations reveal the presence of dust heated by young stars, while X-ray emissions point to hot gas and possible supernova remnants. These multi-wavelength observations are crucial for building a complete picture of the galaxy, as each wavelength provides unique information about the physical processes occurring within it. For example, infrared light can penetrate dust clouds to reveal hidden star-forming regions, while X-rays highlight the most energetic phenomena, such as black hole activity and supernova explosions. The central region of the radiant Gorgon is particularly fascinating due to the interplay between its active galactic nucleus, AGN, and the surrounding starburst activity. The AGN, powered by a supermassive black hole, emits enormous amounts of energy as it accretes matter. This energy output can have a profound impact on the galaxy, heating and expelling gas in a process known as feedback. Feedback is a critical mechanism in galaxy evolution, as it can regulate star formation by either triggering new bursts or quenching ongoing activity. Studying the Medusa's AGN and its effects provides valuable insights into the role of supermassive black holes in shaping their host galaxies. Another compelling aspect of the galactic siren is its chemical complexity. The collision that created the galaxy mixed the gas and dust from the two progenitor galaxies, enriching the interstellar medium with a wide range of elements. Spectroscopic studies of the galaxy have revealed the presence of heavy elements like oxygen, carbon, and iron, which are the byproducts of previous generations of stars. These elements are essential for the formation of planets and life, making the Medusa a key piece in understanding the cosmic cycle of matter. The study of the stellar chimera also sheds light on the larger-scale processes that govern the universe. Merging galaxies like this one are thought to play a significant role in the hierarchical formation of structure, where small systems combine to form larger ones. This process is not only important for individual galaxies but also for galaxy clusters and even the large-scale cosmic web. By studying systems like the Medusa, astronomers can gain insights into how the universe's largest structures came to be. Despite its apparent chaos, the Medusa galaxy is a system in transition, slowly evolving toward a more stable state. As the remnants of the collision settle and the bursts of star formation subside, the galaxy is expected to take on a more elliptical shape. This transformation is a natural part of the life cycle of galaxies and offers a glimpse into the future of similar systems. Observing the Medusa at this stage provides a rare opportunity to study a galaxy in the midst of this transition, offering a snapshot of a process that typically spans billions of years. The celestial serpent also serves as a bridge between the past and future of the cosmos. By studying this galaxy, astronomers can not only learn about the conditions in the early universe but also make predictions about the fate of galaxies like our own Milky Way. The Milky Way's eventual merger with the Andromeda galaxy is expected to produce a system similar to the Medusa, providing a direct connection between these distant cosmic events and our own place in the universe. As technology continues to advance, the Medusa galaxy will remain a focal point for scientific exploration. Next-generation telescopes, such as the James Webb Space Telescope and upcoming ground-based observatories, promise to unveil even more details about this fascinating system. These instruments will allow astronomers to peer deeper into the galaxy, uncovering hidden structures and probing the physical processes at work with unprecedented precision. From its starburst core to its extended tidal tails, the Medusa galaxy offers an endless array of mysteries waiting to be unraveled, ensuring its place as one of the most captivating and scientifically valuable objects in the universe. The Medusa galaxy is a cosmic masterpiece, embodying the complexity and wonder of galactic evolution through its intricate features, dynamic processes, and ongoing transformations. Its chaotic state, caused by the colossal collision of two parent galaxies, has rendered it a perfect example of the interplay between destruction and creation on a universal scale. The aftermath of this collision is not just a spectacle for observation but a living laboratory that reveals critical insights into the forces that shape galaxies, stars, and the very fabric of the universe itself. One of the defining aspects of this galactic chimera is its starburst activity, which remains a primary focus for astronomers. The gravitational interaction between the colliding galaxies has funneled vast amounts of gas and dust into the core, igniting an extraordinary surge of star formation. These regions are dominated by young, massive stars that burn brightly and emit copious amounts of ultraviolet light, ionizing the surrounding gas and creating striking emission nebulae. Studying these starburst regions helps researchers understand the mechanics of star formation under extreme pressures and densities, shedding light on how such processes might have occurred in the early universe. The surrounding environment of the Jellyfish galaxy is equally fascinating. Its extended tidal tails, stretching tens of thousands of light-years into intergalactic space, are composed of stars, gas, and dust ejected during the merger. These tidal structures are often home to their own isolated pockets of star formation, where the conditions differ significantly from those in the galaxy's core. These stellar nurseries in exile provide a unique opportunity to study how star formation occurs in low-density environments, offering a stark contrast to the intense starburst activity in the central regions. The chemical makeup of the nebular hydra is another cornerstone of its scientific significance. During the merger, the interstellar medium was enriched with elements forged in the cores of stars from the parent galaxies. These heavy elements, such as carbon, oxygen, and silicon, are essential for the formation of rocky planets and, ultimately, for the potential emergence of life. By analyzing the spectral signatures of these elements, astronomers can trace the galaxy's chemical evolution and better understand the cosmic processes that distribute the building blocks of life throughout the universe. The Medusa's active galactic nucleus, AGN, is another area of intense interest. The AGN, fueled by a supermassive black hole at the galaxy's center, emits tremendous amounts of energy as it accretes surrounding matter. This activity has profound implications for the galaxy as a whole. The energy output from the AGN can heat the surrounding gas, driving powerful winds that can either trigger or suppress star formation in a process known as AGN feedback. Understanding this feedback mechanism is crucial for unraveling the intricate relationship between supermassive black holes and their host galaxies, a relationship that plays a fundamental role in shaping the universe on both small and large scales. In addition to its AGN activity, the stellar serpent is a source of high-energy phenomena observable in X-rays and radio wavelengths. These emissions are often associated with supernova remnants, neutron stars, and black holes, all of which are abundant in such dynamic environments. By studying these high-energy processes, astronomers can gain insights into the end stages of stellar evolution and the role of extreme astrophysical events in shaping galaxies. The Medusa's chaotic yet mesmerizing structure also serves as a window into the future of our own galaxy. The Milky Way's eventual collision with the Andromeda galaxy will likely produce a system similar to the Medusa, complete with tidal tails, a starburst phase, and an active galactic nucleus. By studying the Medusa, astronomers can make predictions about the sequence of events that will unfold during this future galactic merger and how it will ultimately shape the structure and composition of the resulting galaxy. Beyond its immediate scientific implications, the Medusa galaxy contributes to our broader understanding of the cosmic web, the large-scale structure of the universe. Galaxies like this one are not isolated entities but are influenced by their interactions with neighboring galaxies and the surrounding intergalactic medium. The tidal features of the Medusa provide evidence of these interactions, offering clues about the galaxy's past encounters and its place within the larger cosmic framework. The radiant Gorgon is also a reminder of the universe's inherent beauty, where even the most violent and chaotic events give rise to stunning visual phenomena. Its vivid colors, intricate patterns, and dynamic features captivate both scientists and the public, serving as a powerful tool for inspiring curiosity and engagement with astronomy. The galaxy's striking appearance is a testament to the artistry of nature, where complex physical processes converge to create something both scientifically valuable and aesthetically breathtaking. Looking ahead, the Medusa galaxy remains a prime target for future observations. Next-generation telescopes, such as the Vera Rubin Observatory and the Extremely Large Telescope, ELT, will provide unprecedented views of this enigmatic system. These advanced instruments will allow astronomers to probe deeper into the galaxy's core, resolve its tidal structures with greater clarity, and uncover new details about its interstellar medium, star-forming regions, and AGN activity. Such observations will not only enhance our understanding of the Medusa but also refine our models of galaxy formation and evolution on a universal scale. The continued study of the galactic siren promises to unlock even more secrets about the universe's history and its ongoing transformation. Its chaotic state, though fleeting in cosmic terms, offers a rare glimpse into the processes that have shaped galaxies throughout the cosmos. From its starburst regions to its tidal tails and active nucleus, the Medusa galaxy is a microcosm of the forces that govern the universe, making it an invaluable object of study and a source of endless fascination for scientists and enthusiasts alike. As we unravel its mysteries, the Medusa reminds us of the dynamic and interconnected nature of the cosmos, a place where even the most tumultuous events are part of a larger, harmonious tapestry. The Medusa galaxy captivates not only with its violent origins but also with its profound cosmic implications. Every aspect of this galactic masterpiece tells a story about the transformative forces that govern the universe. Its turbulent evolution reflects the power of galactic mergers, a phenomenon responsible for some of the most dramatic changes in the universe's history. The Medusa is not merely a relic of an ancient collision, it is alive with activity, radiating energy and evolving in real time. The beauty of the Jellyfish galaxy lies in the interplay between chaos and order. Its tangled tidal tails, shimmering with young stars, tell a tale of destruction giving birth to creation. These tidal features stretch far beyond the main galaxy, like celestial tendrils weaving a connection between the Medusa and the vast intergalactic space. Observing these structures reveals how stars and gas can be ejected into the void, where they might seed future star formation in entirely new regions. This process, though seemingly chaotic, is a fundamental mechanism by which galaxies grow and interact with their surroundings. The active starburst regions of the nebular Gorgon are among its most striking features. These areas are like galactic nurseries, where intense gravitational forces compress gas and dust to form massive, luminous stars. These stars live fast and die young, ending their lives in spectacular supernova explosions. Each supernova injects energy and heavy elements into the surrounding medium, enriching it and preparing it for the next wave of star formation. The Medusa, therefore, is not just a snapshot of galactic activity, it is a continuous cycle of birth, death, and rebirth, demonstrating the interconnectedness of all cosmic processes. The central supermassive black hole in the stellar hydra adds another layer of complexity to this fascinating system. Its presence exerts a profound influence on the surrounding galaxy, creating a dynamic interplay between accreting matter and the energy it radiates outward. Jets of high-energy particles are launched from the black hole's poles, cutting through the galaxy and affecting the surrounding gas. These jets can trigger star formation in some regions while quenching it in others, acting as both a creator and destroyer within the galaxy's ecosystem. This duality mirrors the Medusa's mythological namesake, embodying both beauty and danger. The Serpentine Galaxy's rich diversity of stellar populations offers a unique opportunity to study the life cycles of stars. From the blue, young stars in its active regions to the red giants and dying remnants in its outskirts, the Medusa encapsulates every stage of stellar evolution. These populations serve as cosmic time capsules, preserving information about the galaxy's past interactions and star formation history. By analyzing the light from these stars, astronomers can piece together the timeline of events that led to the Medusa's current state, providing a detailed record of its cosmic journey. What makes the radiant chimera even more fascinating is its role as a bridge between different epochs of cosmic history. The conditions within the Medusa resemble those found in the early universe, where frequent mergers and interactions drove rapid star formation. Studying this galaxy allows astronomers to step back in time and understand how similar processes might have shaped the first galaxies. At the same time, the Medusa offers a glimpse into the future, as it provides a model for what might happen when galaxies like the Milky Way and Andromeda eventually collide. The Medusa's turbulent nature also makes it an excellent testbed for studying the physics of interstellar gas. The merger has created a chaotic environment where gas exists in various states, from cold molecular clouds to hot ionized regions. These different phases of gas interact with each other, creating turbulence that influences star formation. Understanding how turbulence shapes the interstellar medium is crucial for explaining why stars form where they do, and the Medusa provides a unique opportunity to study this process in detail. But the story of the galactic siren is not confined to its internal dynamics. It is also a key player in the larger cosmic web, the vast network of galaxies and dark matter that spans the universe. The Medusa's interactions with its surroundings provide clues about how galaxies exchange material with the intergalactic medium. Its tidal tails, for example, may contribute gas and stars to nearby galaxies or serve as a reservoir of material for future interactions. This connectivity underscores the idea that no galaxy exists in isolation, each one is part of a larger cosmic ecosystem. The Medusa galaxy also challenges our understanding of time on a cosmic scale. While its current state appears static in human terms, it is merely a fleeting moment in its evolutionary journey. Over millions of years, the galaxy's tidal tails will dissipate, its starburst activity will wane, and its chaotic structure will settle into a more stable elliptical form. Observing the Medusa today is like catching a snapshot of a dynamic process that has been unfolding for billions of years and will continue long after our own existence. The celestial hydra is more than a scientific curiosity, it is a source of inspiration and wonder. Its breathtaking appearance, with its vivid hues and intricate patterns, reminds us of the universe's capacity for creating beauty out of chaos. For astronomers, it represents a treasure trove of knowledge, a place where they can study the forces that have shaped the cosmos. For the public, it is a symbol of the vastness and complexity of the universe, sparking curiosity and a sense of connection to the cosmos. As technology advances, the Medusa galaxy will remain a focal point for exploration and discovery. Future missions, such as those using the European Space Agency's Athena X-ray Observatory or next-generation radio telescopes, will uncover new details about this enigmatic system. These observations will deepen our understanding of everything from black hole physics to the large-scale structure of the universe. The Medusa, with its rich tapestry of phenomena, will continue to inspire new questions and drive the quest for answers, ensuring its place as one of the most scientifically valuable and awe-inspiring objects in the night sky. Through the Medusa galaxy, we are reminded of the universe's infinite complexity and its capacity for transformation. It is a living testament to the forces of change, a cosmic dance where destruction and creation are intertwined. As we continue to study this remarkable galaxy, we are not just learning about a distant object, we are uncovering the story of the universe itself, a story that includes our own origins and our place within the grand cosmic web. The Medusa galaxy stands as a cosmic stage where the grand forces of the universe play out their intricate roles. It is a living illustration of how galaxies evolve through time, shaped by the interplay of gravity, turbulence, and the relentless push and pull of interstellar material. What makes this system truly remarkable is its ability to combine these dramatic processes into a cohesive, albeit chaotic, masterpiece of science and art. One of the most captivating aspects of the Jellyfish galaxy is the sheer scale and energy of its starburst activity. Within its core lies a seething cauldron of star formation, where gas and dust collapse under intense gravitational forces to form clusters of massive stars. These stars, in turn, light up their surroundings with ultraviolet radiation, ionizing the gas and creating vast bubbles of glowing plasma. The winds and shock waves generated by these stars further compress nearby gas clouds, triggering a chain reaction of star formation. This feedback loop is a vital piece of the puzzle in understanding how galaxies sustain and regulate star formation over time. The tidal tales of the nebular serpent continue to offer insights into the aftermath of galactic collisions. These vast streams of stars and gas are essentially the cosmic fingerprints left behind by the gravitational interaction of the parent galaxies. They stretch outward into intergalactic space, carrying with them valuable clues about the Medusa's past. Embedded within these tales are small, dense regions where stars are still forming, providing a unique environment that contrasts sharply with the crowded, high-pressure starburst regions in the galaxy's core. These remote pockets of star formation allow astronomers to study how stars can arise in low-density regions, offering a new perspective on the diversity of star-forming conditions in the universe. The radiant chimera also provides a window into the complex interplay between its central supermassive black hole and its surrounding environment. The black hole, a voracious force at the heart of the galaxy, feeds on gas and dust pulled toward its event horizon. This process generates immense energy, which is released in the form of jets and outflows that ripple through the galaxy. These high-energy phenomena are not just destructive, they play a crucial role in shaping the galaxy's structure by redistributing gas, regulating star formation, and even enriching the intergalactic medium with heavy elements. The Medusa galaxy, therefore, is a prime example of how black holes influence not only their immediate surroundings but also the larger-scale evolution of their host galaxies. Another intriguing feature of the stellar hydra is the role of its dust and molecular clouds. Dust grains, though tiny on an individual scale, collectively act as the cosmic glue that binds together the ingredients for star formation. These grains absorb and scatter light, obscuring parts of the galaxy when viewed in optical wavelengths but glowing brightly in the infrared. Observing the Medusa in these longer wavelengths reveals a hidden world of activity, where dense molecular clouds are collapsing to form the next generation of stars. This ability to study the invisible aspects of the galaxy is a testament to the power of modern observational technology, which continues to peel back the layers of mystery surrounding systems like the Medusa. The Serpentine Galaxy is also a case study in the chemical enrichment of the cosmos. The heavy elements forged in the cores of stars and released through supernova explosions are dispersed throughout the galaxy, enriching its gas and dust with the building blocks of planets and, potentially, life. Spectroscopic studies of the Medusa have revealed a rich tapestry of elements, including carbon, oxygen, and nitrogen, which are vital for the development of complex organic molecules. By tracing the distribution and abundance of these elements, astronomers can piece together the history of star formation and chemical evolution within the galaxy. On a larger scale, the Medusa galaxy serves as a microcosm for understanding the hierarchical nature of cosmic structure. Its collision and subsequent evolution are part of a broader narrative in which small systems merge to form larger ones, a process that has shaped the universe from its earliest days. The Medusa's current state, with its chaotic appearance and intense activity, offers a snapshot of this process in action, allowing astronomers to study the mechanisms that drive the growth of galaxies and the larger cosmic web. The chaotic beauty of the celestial hydra also has profound implications for the study of time in the universe. The tidal tails and starburst regions we observe today are the direct results of events that unfolded millions of years ago. Light from the Medusa takes 130 million years to reach us, meaning that we are witnessing the galaxy as it existed during the age of the dinosaurs on Earth. This temporal disconnect highlights the vast scales of time and space that define the universe, reminding us of our own fleeting moment in cosmic history. In addition to its scientific significance, the Medusa galaxy is a beacon of inspiration for humanity. Its vivid colors, intricate structures, and dynamic processes captivate the imagination, serving as a powerful reminder of the universe's boundless creativity. The galaxy's very existence challenges us to think beyond the confines of our own planet and to consider the larger forces at work in shaping the cosmos. It is a testament to the ingenuity of human exploration that we can study such distant and complex systems, uncovering their secrets and expanding our understanding of the universe. As we continue to probe deeper into the mysteries of the radiant Gorgon, new discoveries are certain to emerge. Upcoming missions and observatories, equipped with cutting-edge technology, promise to reveal even more about the galaxy's hidden features and the processes driving its evolution. From the faintest stars in its tidal tails to the energetic jets emanating from its central black hole, the Medusa galaxy remains a treasure trove of scientific opportunity, a cosmic jewel whose mysteries will keep astronomers enthralled for generations to come. The Medusa is a reminder that the universe is a place of constant change and transformation. Its story is one of destruction and creation, chaos and order, beauty and power. In studying this galaxy, we not only learn about its unique characteristics but also uncover universal truths about the forces that shape the cosmos. The Medusa galaxy, in all its complexity, is a testament to the resilience and interconnectedness of the universe, a timeless symbol of the eternal dance of the stars. The Medusa galaxy's dynamic nature ensures it remains a central focus in the study of galactic evolution. Its story is one of endless change, revealing the universe's capacity for both destruction and renewal. Each feature, from its luminous starburst core to its vast tidal tails, offers a piece of the puzzle, helping astronomers decode the mechanisms that have shaped galaxies across billions of years. The Medusa is not just a snapshot of cosmic evolution, it is a window into the processes that define the life cycles of galaxies, providing an unparalleled opportunity to study the forces at work in the cosmos. The ongoing star formation in the Jellyfish galaxy serves as a testament to the transformative power of galactic collisions. These processes compress interstellar gas to densities that ignite star formation on an extraordinary scale. The galaxy's central regions, where these processes are most intense, shine with the brilliance of countless young, massive stars. These stars burn hot and fast, emitting streams of radiation and powerful stellar winds that shape the surrounding environment. Their lifespans are brief in cosmic terms, often ending in supernova explosions that release heavy elements and energy into the interstellar medium. Each explosion enriches the galaxy, seeding the material necessary for the next generation of stars and planets. Meanwhile, the Medusa's tidal tails are not merely remnants of its violent past but active regions of transformation. These extended arms of stars and gas stretch across tens of thousands of light-years, containing clumps of material dense enough to form stars. In these distant outposts, removed from the central starburst, star formation proceeds at a more sedate pace, creating a striking contrast between the chaotic core and the serene outskirts. These regions also provide insight into how material expelled during collisions contributes to the broader galactic ecosystem, as these streams often interact with neighboring galaxies or feed into the intergalactic medium. One of the most intriguing aspects of the nebular Gorgon is its central supermassive black hole, a colossal entity that exerts a profound influence on the galaxy. The black hole's gravitational pull drives the accretion of surrounding gas and dust, generating immense amounts of energy as this material is heated to extreme temperatures. The resulting jets and outflows of energy ripple through the galaxy, shaping its structure and regulating star formation. These feedback mechanisms are a crucial component of galactic evolution, as they can suppress star formation by expelling gas or, conversely, trigger new starbursts by compressing gas in certain regions. The Medusa offers a rare opportunity to study these effects in detail, helping astronomers understand how black holes and galaxies co-evolve. The study of the stellar hydra's interstellar medium further deepens our understanding of the galaxy's complex processes. The collision that birthed the Medusa created a highly turbulent environment where gas exists in a variety of states, from cold molecular clouds to hot ionized regions. These different phases interact in complex ways, creating a dynamic medium where star formation and feedback processes constantly reshape the galaxy. Observations at different wavelengths, from radio to X-rays, allow astronomers to map these interactions and gain insight into the physical conditions that drive galactic evolution. The chemical richness of the Serpentine galaxy is another key area of study. The heavy elements dispersed by previous generations of stars are now a fundamental part of the galaxy's makeup, influencing everything from star formation to the development of planetary systems. By analyzing the spectra of light emitted by the galaxy, astronomers can trace the distribution and abundance of these elements, piecing together the history of chemical enrichment that has occurred over billions of years. This chemical legacy is not just a feature of the Medusa itself but a contribution to the cosmic ecosystem, as the galaxy's interactions with its surroundings disperse these elements into the intergalactic medium. The Medusa also offers a glimpse into the broader cosmic web, the vast network of galaxies, dark matter, and intergalactic gas that spans the universe. Its tidal tails and interactions with nearby galaxies are part of this larger structure, illustrating the interconnectedness of galaxies within clusters and superclusters. These interactions are not isolated events but part of a larger narrative in which galaxies grow and evolve through mergers and exchanges of material. The Medusa's place within this web highlights the importance of understanding not just individual galaxies but their roles within the broader cosmic context. The celestial hydra's current state, though chaotic, is only a transitional phase in its long evolutionary journey. Over time, the intense starburst activity will subside as the available gas is consumed or expelled, and the galaxy will settle into a more stable configuration, likely taking on the elliptical shape typical of post-merger systems. This transformation offers a glimpse into the long-term effects of galactic collisions, providing a model for understanding the eventual fate of galaxies like our own Milky Way, which is destined to merge with the Andromeda galaxy in a similar event. What makes the radiant chimera so captivating is not just its scientific significance but its ability to inspire wonder and curiosity. Its striking appearance, with vibrant colors and intricate structures, serves as a reminder of the universe's boundless creativity. For astronomers, it represents a treasure trove of data, a system where countless physical processes can be studied in detail. For the public, it is a symbol of the universe's majesty, sparking a sense of connection to the cosmos and a desire to explore its mysteries further. As technology advances, the Medusa galaxy will remain at the forefront of astronomical research. New telescopes and observatories, equipped with cutting-edge instruments, will allow us to probe deeper into this enigmatic system, uncovering hidden features and revealing new aspects of its nature. From its turbulent core to its serene outskirts, the Medusa promises to continue providing valuable insights into the forces that shape galaxies and the universe as a whole. The Medusa galaxy, in all its complexity, reminds us of the dynamic and ever-changing nature of the cosmos. It is a living testament to the universe's capacity for transformation, a place where destruction gives rise to creation, and chaos leads to beauty. Through the study of this remarkable galaxy, we not only expand our understanding of the universe but also gain a deeper appreciation for the intricate processes that have shaped our own cosmic home. The Medusa is more than a galaxy, it is a cosmic masterpiece, a source of endless fascination, and a symbol of the universe's eternal dance of change. The Medusa galaxy, or NGC 4194, offers an almost inexhaustible reservoir of phenomena to investigate, particularly in the realm of astrophysics. Its chaotic yet coherent structure is a rich tapestry woven from the interaction of gravitational forces, thermodynamics, and chemical processes. Each layer of its complexity reveals fundamental insights into the processes that shape galaxies throughout the cosmos. At its core, the Medusa galaxy is a laboratory for understanding the intricate mechanisms governing galaxy formation, evolution, and interaction. A key area of scientific inquiry in the Medusa galaxy is its molecular gas content, which serves as the primary fuel for star formation. Observations at submillimeter wavelengths, such as those conducted by instruments like ALMA, Atacama Large Millimeter/Submillimeter Array, have revealed vast reservoirs of cold molecular hydrogen, H2, concentrated in the central regions of the galaxy. These gas clouds, often containing traces of carbon monoxide, CO, that make them detectable, are subjected to intense gravitational compression during the merger process. The resulting high densities lead to efficient star formation, transforming these reservoirs into clusters of massive, short-lived stars. Studying the properties of molecular gas in the Medusa provides insight into how galactic collisions enhance star formation and how these processes compare to quiescent galaxies. The dynamics of the interstellar medium, ISM, in the Medusa galaxy are another focus of intense study. The collision has created an environment where turbulence dominates, with gas flowing in streams, eddies, and shocks. This turbulence plays a dual role. While it prevents some regions of the gas from collapsing into stars, it also compresses other regions, triggering star formation. Understanding how turbulence operates in such an extreme environment is critical for building models of star formation, as it bridges the gap between small-scale physics within molecular clouds and large-scale galactic dynamics. Beyond the ISM, the Medusa's starburst activity provides a wealth of data for understanding the interplay between newly formed stars and their environment. Massive stars emit intense ultraviolet radiation that ionizes nearby gas, creating regions of ionized hydrogen, H2 regions. These regions glow brightly in visible light, particularly in specific emission lines like H-alpha, which can be used to map the spatial distribution of star formation across the galaxy. Simultaneously, the winds from these stars, along with the eventual supernova explosions, inject energy into the surrounding medium, driving outflows of gas. These outflows, sometimes referred to as galactic winds, are critical for regulating star formation by removing gas from the central regions and enriching the surrounding intergalactic medium with metals. The Medusa's active galactic nucleus, AGN, adds yet another layer of complexity. Powered by accretion onto a supermassive black hole, the AGN emits radiation across the electromagnetic spectrum, from radio waves to X-rays. This activity can have profound effects on the galaxy, both locally and on larger scales. High-energy photons and relativistic particles from the AGN can heat and ionize gas, potentially suppressing star formation in the immediate vicinity. However, In some cases, AGN-driven outflows can compress gas clouds and trigger star formation at larger distances. This dual role of AGN feedback makes it a key area of research, particularly in systems like the Medusa where both AGN and starburst activity are present. The chemical enrichment of the Medusa galaxy is another scientific frontier. The heavy elements created in stars and dispersed through supernova explosions enrich the galaxy's interstellar medium, altering the composition of future generations of stars and planets. By analyzing the galaxy's spectral lines, astronomers can determine the abundance of elements like oxygen, carbon, nitrogen, and iron, which are key indicators of a galaxy's evolutionary state. These observations help build a timeline of star formation and chemical evolution, offering clues about the progenitor galaxies that collided to form the Medusa. The tidal features of the Medusa, particularly its extended tails of stars and gas, provide critical evidence of the galaxy's violent origins. These tidal tails are formed by gravitational forces during the collision, pulling material outward into intergalactic space. Detailed studies of these structures can reveal the masses and trajectories of the colliding galaxies, as well as the distribution of dark matter within the system. Additionally, the star clusters found within these tails represent a unique environment for studying star formation outside the dense environments of galactic cores. Another fascinating aspect of the Medusa galaxy is its multi-wavelength signature. Each wavelength probes a different physical process within the galaxy. For instance, radio observations trace cold molecular gas, infrared observations reveal warm dust heated by young stars, optical wavelengths highlight ionized gas and stellar populations, and X-rays capture the high-energy processes associated with the AGN and supernova remnants. Combining data from these wavelengths creates a comprehensive picture of the galaxy, allowing astronomers to study its various components in unprecedented detail. The Medusa's relevance extends beyond its individual characteristics to its role in the broader context of cosmic evolution. Galaxy mergers, such as the one that created the Medusa, are thought to play a significant role in the hierarchical growth of structure in the universe. By observing systems like the Medusa at different stages of their evolution, astronomers can piece together the sequence of events that leads to the formation of massive elliptical galaxies, the end state for many merging systems. These observations are also crucial for understanding the future evolution of our own Milky Way, which is expected to merge with the Andromeda galaxy in several billion years. Moreover, the Medusa galaxy provides a valuable test case for numerical simulations of galaxy mergers. By comparing observations of the Medusa with the results of simulations, astronomers can refine their models, improving our understanding of the physical processes involved in such interactions. These simulations incorporate a wide range of phenomena, including gravity, hydrodynamics, star formation, feedback from stars and black holes, and the influence of dark matter. The Medusa's detailed observational data serve as a benchmark for testing these complex models, helping to bridge the gap between theoretical predictions and real-world observations. In summary, the Medusa galaxy is not just an object of astronomical beauty but a cornerstone for scientific discovery. Its unique combination of features, intense starburst activity, a turbulent interstellar medium, an active nucleus, and extended tidal structures, makes it a microcosm of the processes that shape galaxies throughout the universe. As technology continues to advance, enabling more detailed observations and sophisticated simulations, the Medusa will undoubtedly remain a focal point for research, offering new insights into the forces that drive the cosmos. Its story, one of chaos, transformation, and renewal, mirrors the larger narrative of the universe itself, a testament to the intricate and dynamic nature of the cosmos. The Medusa galaxy remains an unending source of scientific exploration, not only due to its present structure but also because of the insights it provides into the universal laws governing galaxies and their evolution. Its story is a cosmic narrative of gravity, turbulence, stellar feedback, and chemical enrichment that unfolds across multiple dimensions of time and space. Each element within this galactic system adds to our understanding of the mechanisms that build, sustain, and ultimately transform galaxies. One particularly compelling aspect of the Medusa is its role as a natural experiment in gravitational physics. Galactic collisions like the one that formed NGC 4194 occur under the influence of dark matter halos that envelop each galaxy. These halos, made of invisible and mysterious dark matter, govern the overall dynamics of the merger. By studying the motion of stars and gas within the Medusa, astronomers can indirectly map the distribution of dark matter and gain critical insights into its properties. For instance, the gravitational effects seen in the tidal tails and the overall kinematics of the system provide evidence of how dark matter influences galaxy formation and interaction on both local and cosmic scales. The tidal structures of the Medusa are also prime sites for studying gravitational instabilities. The collision has stretched and redistributed material across enormous distances, creating localized regions of enhanced density where star formation has been triggered. These clumps, often referred to as tidal dwarf galaxies or proto-galaxies, are fascinating laboratories for understanding how gravitational forces can condense material into new structures. Unlike their parent galaxies, these smaller systems are often dominated by recently formed stars and contain relatively little dark matter, challenging traditional models of galaxy formation. Beyond its gravitational dynamics, the Medusa galaxy is a hotbed of hydrodynamic processes. The merger has created an environment where interstellar gas flows are compressed, shock-heated, and rapidly mixed. These processes are best studied through high-resolution hydrodynamic simulations, which can replicate the chaotic flows observed in the Medusa. Shock fronts, in particular, play a critical role in triggering star formation by compressing gas into dense, star-forming filaments. By comparing simulations with observations, astronomers can refine their models of how shock waves and turbulence influence star formation, not just in mergers but in galaxies across the universe. The Medusa also offers a unique perspective on the life cycle of dust, an often overlooked yet vital component of galaxies. Dust grains, formed in the atmospheres of dying stars and supernovae, play a crucial role in cooling interstellar gas and enabling star formation. However, the extreme conditions in the Medusa, including powerful stellar winds, radiation pressure, and supernova shocks, subject dust to destruction and recycling processes. Infrared observations reveal how dust survives, evolves, and interacts with its environment in such harsh conditions. These studies are essential for understanding how dust contributes to the chemical and thermal balance of the interstellar medium. On larger scales, the Medusa galaxy exemplifies the role of feedback in regulating star formation. Feedback processes, driven by both stars and the central supermassive black hole, inject energy and momentum into the surrounding gas, creating outflows that can escape the galaxy's gravitational pull. These galactic winds carry metals into the intergalactic medium, enriching it with heavy elements that are crucial for the next generation of stars and planets. Observations of these outflows in the Medusa, particularly at X-ray and ultraviolet wavelengths, reveal their structure, composition, and impact on the galaxy's evolution. By studying the energy budget and efficiency of these processes, astronomers gain insights into how galaxies self-regulate their growth and star-forming activity. The Medusa's supermassive black hole, a dominant force in its central regions, further complicates the feedback picture. High-energy emissions from the black hole are thought to influence gas dynamics on scales ranging from a few light-years to tens of thousands of light-years. These emissions, often in the form of relativistic jets or ionized gas outflows, interact with the galaxy's interstellar medium in complex ways. In some cases, the energy released by the black hole heats the gas, preventing it from collapsing into stars, a phenomenon known as quenching. In others, the outflows compress gas clouds, triggering star formation at the edges of expanding shock fronts. The Medusa's combination of AGN activity and intense starburst regions provides a rare opportunity to study how these competing processes interact in real time. A particularly fascinating area of ongoing research involves the Medusa's role in the cosmic baryon cycle. Galaxies do not exist in isolation but are deeply interconnected with their surrounding environment through the exchange of gas and energy. The tidal tails and outflows of the Medusa contribute material to the intergalactic medium, while inflows of gas from the surrounding cosmic web replenish its star-forming reservoirs. This continuous exchange is a fundamental part of galaxy evolution, influencing everything from star formation rates to the growth of dark matter halos. Observing these exchanges in the Medusa provides a window into how galaxies maintain their activity over billions of years. The Medusa's importance is magnified when considered in the context of its potential future. The galaxy is currently in a transitional phase, evolving from the chaotic aftermath of its merger toward a more stable state. Over time, its intense starburst activity will diminish as its gas reservoirs are depleted or expelled. Eventually, the galaxy will settle into a quiescent elliptical form, dominated by older stars and lacking the dramatic features of its current state. This evolution mirrors the fate of many merging galaxies, offering a glimpse into the long-term processes that shape the universe's population of galaxies. From a cosmological perspective, the Medusa galaxy provides critical evidence for the hierarchical nature of galaxy formation. Its chaotic structure, active star formation, and tidal features are hallmarks of the processes that build larger structures from smaller components. These processes were even more common in the early universe, where galaxies were smaller and interactions more frequent. By studying the Medusa, astronomers can draw direct parallels to the conditions that shaped the first galaxies, bridging the gap between the ancient past and the present-day universe. As observational technology advances, the Medusa galaxy will continue to serve as a focal point for scientific discovery. Upcoming missions like the Square Kilometre Array, SKA, will enable detailed studies of its neutral hydrogen gas, mapping the large-scale flows that drive its evolution. Similarly, next-generation space telescopes such as the James Webb Space Telescope, JWST, and the planned Louvre Observatory will probe the Medusa's star-forming regions and AGN activity with unprecedented resolution and sensitivity. These observations will not only enhance our understanding of the Medusa itself but also refine our models of galaxy formation and evolution across the cosmos. Ultimately, the Medusa galaxy is far more than a cosmic curiosity, it is a cornerstone for understanding the universe. Its dynamic interplay of forces, from gravitational interactions to stellar feedback, encapsulates the complexity of the cosmos in a single system. By studying this remarkable galaxy, we uncover the universal principles that govern all galaxies, shedding light on the processes that have shaped the universe from its earliest moments to the present day. The Medusa is a testament to the beauty, complexity, and interconnectedness of the cosmos, a vivid reminder that even in chaos, the universe creates order and wonder. The Medusa galaxy continues to be a cornerstone of astrophysical research, offering profound insights into the processes that drive galaxy evolution. Its turbulent nature serves as a microcosm of universal phenomena, where the interplay between gravity, star formation, and feedback mechanisms unfolds on scales spanning light-years to tens of thousands of light-years. Scientists view the Medusa as a dynamic laboratory for testing theories about galactic mergers, stellar birth and death, and the enrichment of the cosmos with heavy elements. A pivotal area of exploration in the Medusa galaxy is its interstellar medium, ISM, which has been violently reshaped by the collision that created it. The ISM in the Medusa exists in multiple phases: cold molecular gas, warm atomic gas, and hot ionized gas. These phases interact dynamically, exchanging energy and momentum through processes such as shock compression, turbulence, and radiative cooling. The collision has amplified these interactions, creating regions of intense star formation in areas where gas is stripped away, leaving voids. This highly disturbed ISM allows astronomers to study how energy and matter flow through galaxies and how these flows influence the life cycle of stars. One key feature of the Medusa's ISM is its reservoirs of cold molecular gas, which serve as the raw material for star formation. Observations with radio telescopes, such as ALMA, have detected vast clouds of molecular hydrogen, H2, concentrated in the central regions of the galaxy. These clouds are often traced using carbon monoxide (CO) emissions, which act as a proxy for the presence of molecular hydrogen. The extreme pressures and densities in these regions have triggered bursts of star formation, resulting in the formation of massive star clusters. Understanding how these dense molecular clouds collapse to form stars in such a chaotic environment provides vital clues about the conditions required for star formation, both in merging galaxies and in the broader universe. The Medusa galaxy's starburst regions, particularly in its core, are among the most luminous and active in the local universe. These regions are powered by the rapid formation of massive stars, which emit intense ultraviolet radiation that ionizes the surrounding gas. This ionized gas forms glowing regions known as H2 regions, which are key tracers of star formation activity. The size, luminosity, and distribution of these regions in the Medusa provide a detailed map of where star formation is most active and how it correlates with the dynamics of the galaxy. By studying the physical properties of these H2 regions, astronomers can better understand how the star formation rate is regulated in extreme environments. The stellar feedback from the newly formed stars in the Medusa is another area of active investigation. Massive stars have relatively short lifespans, often ending in spectacular supernova explosions that release vast amounts of energy into the surrounding medium. These explosions generate shock waves that compress nearby gas, potentially triggering new waves of star formation. At the same time, the energy released can heat and disperse gas, reducing the efficiency of future star formation. Observations of the Medusa have revealed evidence of both processes occurring simultaneously, providing a unique opportunity to study how stellar feedback shapes the evolution of galaxies. The Medusa's active galactic nucleus, AGN, adds another layer of complexity to this already dynamic system. Powered by a supermassive black hole at the galaxy's center, the AGN emits energy across the electromagnetic spectrum, from radio waves to X-rays. This energy output is driven by the accretion of gas onto the black hole, which forms a hot, rotating disk around it. The AGN's powerful radiation and relativistic jets interact with the surrounding ISM, heating gas and driving large-scale outflows. These outflows, often referred to as galactic winds, can have profound effects on the galaxy's evolution by removing gas that would otherwise fuel star formation. The Medusa's AGN provides a critical case study for understanding how these feedback mechanisms operate in galaxies experiencing simultaneous AGN activity and starbursts. Another fascinating aspect of the Medusa galaxy is its chemical evolution. The heavy elements, or metals, present in the galaxy are the products of nucleosynthesis in stars. When stars die, particularly in supernova explosions, they release these metals into the ISM, enriching it with elements like oxygen, carbon, and iron. Observations of the Medusa have revealed high metallicities in its central regions, consistent with the intense star formation and supernova activity occurring there. By studying the distribution of metals in the Medusa, astronomers can trace the processes that have enriched the galaxy over time and compare them to those in other merging systems. The tidal tails of the Medusa galaxy are another focus of scientific attention. These long, sweeping structures are composed of stars, gas, and dust that were gravitationally stripped from the galaxy during the merger. Tidal tails are rich with clues about the history of the interaction, including the masses and orbital dynamics of the progenitor galaxies. Embedded within these tails are dense clumps of gas and young stars, some of which may evolve into independent systems, known as tidal dwarf galaxies. These structures are valuable for studying star formation in low-density environments and for understanding the role of tidal interactions in galaxy evolution. From a cosmological perspective, the Medusa galaxy is a window into the processes that shaped the early universe. In the first few billion years after the Big Bang, galaxy mergers were far more common, as galaxies were smaller and more densely packed. The Medusa's chaotic state, intense star formation, and active nucleus mirror the conditions that would have been typical in this era. By studying the medusa, astronomers can draw parallels to the formation of the first galaxies, shedding light on how the universe evolved from a chaotic, primordial state to the structured cosmos we see today. The Medusa galaxy also plays a role in the broader cosmic ecosystem. Its tidal tails and galactic winds contribute material to the intergalactic medium, IGM, enriching it with metals and energy. This material can later be accreted by other galaxies, continuing the cycle of enrichment and evolution. Observing how the Medusa exchanges matter and energy with its surroundings provides valuable insights into the interconnected nature of galaxies and the larger cosmic web. Future observations of the Medusa galaxy promise to unlock even more of its secrets. Instruments like the James Webb Space Telescope, JWST, and next-generation ground-based observatories will provide unprecedented views of the galaxy's core, tidal structures, and star-forming regions. These observations will reveal the physical processes driving the Medusa's evolution with unprecedented clarity, offering new opportunities to test theories about galaxy formation and interaction. In conclusion, the Medusa galaxy is far more than a visual marvel. It is a scientific treasure trove that encapsulates the fundamental processes shaping galaxies across the cosmos. Its chaotic yet beautiful structure serves as a living laboratory for exploring the laws of physics, the life cycles of stars, and the evolution of the universe itself. As we continue to study the Medusa, we not only deepen our understanding of this remarkable galaxy but also uncover the universal principles that govern the cosmos, connecting us to the grand narrative of creation and transformation that defines the universe. The Medusa galaxy, with its turbulent and transformative nature, remains a profound example of the cosmos' relentless capacity for change and adaptation. As astronomers delve deeper into its structure, the galaxy reveals a multitude of complex processes operating on every conceivable scale, from the microscopic interactions of particles in the interstellar medium to the grand dynamical movements of entire stellar populations. Each layer of the Medusa's anatomy presents opportunities to explore the physics that govern not only its own evolution but the evolution of galaxies throughout the universe. One of the central themes in studying the Medusa galaxy is understanding the physics of shock waves generated by its galactic collision. These shock waves, which propagate through the interstellar medium at supersonic speeds, play a critical role in heating and compressing gas clouds. Observations in X-ray and radio wavelengths reveal the presence of these shock fronts, which often light up in emission lines characteristic of ionized gases. By analyzing these emissions, astronomers can determine the temperature, density, and velocity of the shocked gas, offering insights into the energy dissipation mechanisms at work. This knowledge is vital for understanding how such violent events can both trigger and inhibit star formation, depending on local conditions. In addition to shocks, the turbulent nature of the Medusa's ISM provides a unique opportunity to study turbulence in astrophysical plasmas. Turbulence within galaxies is thought to cascade energy from large to small scales, creating intricate structures within molecular clouds. These turbulent motions contribute to the fragmentation of gas clouds, which ultimately leads to the formation of stars. The Medusa's highly disturbed environment amplifies these processes, making it an ideal testbed for studying the transition from large-scale galactic dynamics to small-scale star-forming cores. Numerical simulations, combined with multi-wavelength observations, help astronomers model these turbulent flows, providing a deeper understanding of how turbulence shapes the life cycle of galaxies. Another fascinating aspect of the Medusa galaxy is the role of magnetic fields in its evolution. While often overlooked, magnetic fields can influence the dynamics of gas and dust within galaxies. Observations using radiopolarimetry can detect synchrotron radiation emitted by relativistic electrons spiraling around magnetic field lines, revealing the structure and strength of these fields. In the Medusa, magnetic fields may play a role in channeling gas flows, aligning dust grains, and even affecting the propagation of cosmic rays. Understanding these effects is crucial for developing a comprehensive picture of how galaxies like the Medusa evolve over time. The Medusa's starburst regions also provide a laboratory for studying feedback from massive stars. These stars, often grouped into massive star clusters, generate intense stellar winds and ultraviolet radiation fields that shape their surroundings. The energy injected by these feedback processes can drive large-scale galactic outflows, contributing to the regulation of star formation and the enrichment of the intergalactic medium. These outflows, observed as expanding bubbles and shells in the Medusa, carry information about the energy output of the starburst and the efficiency of feedback mechanisms. Measuring the kinematics and composition of these outflows allows astronomers to quantify the impact of stellar feedback on galaxy evolution. Furthermore, the Medusa's central active galactic nucleus, AGN, offers a rare chance to study the coevolution of supermassive black holes and their host galaxies. The AGN's powerful radiation not only affects the surrounding gas but also interacts with the galaxy's magnetic fields, influencing the morphology and dynamics of the ISM. High-resolution spectroscopy across various wavelengths, ranging from optical to X-ray, allows astronomers to dissect the AGN's emission mechanisms, revealing the accretion processes at work. By understanding how the AGN influences its host galaxy, scientists can better comprehend the symbiotic relationship between black hole growth and galactic evolution. The chemical evolution of the Medusa galaxy is also a critical area of study. The intense star formation activity enriches the ISM with heavy elements, or metals, which are synthesized in the cores of stars and dispersed through supernova explosions. Detailed spectroscopic analyses reveal the abundance gradients of these elements across the galaxy, providing a timeline of chemical enrichment. This, in turn, informs models of star formation efficiency and the initial mass function, IMF, within starburst galaxies. By comparing these observations with theoretical models, astronomers can trace the pathways through which galaxies like the Medusa evolve chemically over billions of years. Another intriguing phenomenon observed in the Medusa is the presence of high-velocity clouds, HVCs, which are massive blobs of gas moving at velocities significantly different from the galaxy's disk rotation. These HVCs may represent infalling material from the cosmic web, contributing fresh gas that sustains star formation, or they might be remnants of past galactic interactions. Studying these clouds can provide insights into the processes of galactic accretion and recycling, critical for understanding long-term galaxy evolution. On a cosmological scale, the Medusa galaxy serves as a snapshot of a pivotal stage in galaxy evolution. It exemplifies how galactic mergers contribute to the hierarchical assembly of structure in the universe. By observing the Medusa, astronomers gain a better understanding of how small protogalaxies merge and coalesce into the massive galaxies observed today. The Medusa's current chaotic state mirrors the conditions of the early universe when galaxy mergers were more frequent, thus offering a rare glimpse into the past epochs of cosmic evolution. Future observations with upcoming facilities like the 30-meter telescope, TMT, and the European Extremely Large Telescope, EELT, will allow astronomers to resolve even finer details within the Medusa. Adaptive optics systems will provide sharper images of its star-forming regions and AGN, while advanced spectrographs will dissect its chemical composition and kinematics with unprecedented precision. These observations will enable a more detailed understanding of the physical processes driving the Medusa's evolution. In addition, simulations using next-generation supercomputers will model the complex interactions observed in the Medusa. These simulations incorporate not only gravitational dynamics but also hydrodynamics, magnetohydrodynamics, and radiative transfer, offering a multi-scale, multi-physics approach to galaxy evolution. By comparing these models with observational data, astronomers can refine their theories of galaxy formation and feedback mechanisms, bridging the gap between theoretical predictions and empirical observations. In summary, the Medusa galaxy is a dynamic and evolving system that encapsulates the myriad processes governing galaxy evolution. Its rich tapestry of interactions, from stellar feedback to AGN activity and chemical enrichment, provides a comprehensive view of the forces that shape galaxies. As technology advances, the Medusa will remain a cornerstone for astrophysical research, continually revealing the intricate and interconnected nature of the universe. Through its study, we not only unlock the secrets of a single galaxy but also gain profound insights into the workings of the cosmos itself, a testament to the enduring power of scientific exploration. The Medusa Galaxy, in all its chaos and complexity, is a profound testament to the dynamism of the cosmos. It stands as a living reminder that the universe is a place of constant motion, transformation, and interplay between destruction and creation. The Medusa is not merely a product of its past, a violent collision that birthed its tumultuous features, but also a harbinger of its future, one that encapsulates the life cycle of galaxies on both micro and macro scales. Its central starburst regions, ignited by the compression of gas during the merger, represent the raw power of gravitational interactions. Here, the seeds of new stars are planted in the wake of cosmic violence, shining as beacons of renewal. These young stars live brief but brilliant lives, enriching the surrounding medium with heavy elements when they die in supernova explosions. This cycle of birth, life, and death plays out on a galactic scale, weaving the intricate tapestry of the Medusa's evolving structure. Each generation of stars contributes to the enrichment of the interstellar medium, laying the foundation for the future development of stars, planets, and, potentially, the conditions necessary for life. The tidal tails of the Medusa stretch out like cosmic arms, connecting the galaxy to its broader environment and to its past. These tails, composed of stars and gas pulled away by tidal forces, tell the story of the violent merger that shaped the galaxy. They are not merely remnants of destruction but zones of ongoing creation, where star clusters form in the low-density outskirts, unbound by the constraints of the galactic core. These features serve as a bridge between the Medusa and the intergalactic medium, facilitating